Hi, this is Tim, and welcome to Talks with Tim Improvised. So the power went out, and then we found out there was a pole on fire, and then it had set all the trees around on fire, so the fire department was there, and it looked like it would be quite a while. We're going to take a little more time getting this one started. Michael, do I have sound? Do I have all the fun things?
Yes, you have sound.
Oh my goodness. Michael is amazing here. I mean... Here we there. You know, a couple things. For anybody that thinks that my videos are scripted, yeah, watch me now because, yeah, they're not usually scripted. We kind of have a rough idea of what we're going to do. And, yeah, Michael just managed to race back here in, what, how long has it been? 30 minutes maybe? And it is completely set up at a different location, and everything seems to be working. So, yes, Jeff Kuiper is back. And, man, I really hate that because... One, we got a lot. We got a lot of good info planned. Now you're going to hear a lot of shuffling, a lot of moving around because really we just started dumping things into a bag and getting going. But the cool thing for everybody that is in there is we are going to be giving away a PLC Tools Sim ALB2 analog simulator to someone who is participating in the chat. And just like last time, participation in the chat doesn't mean hi. It means you ask a question about milliamps or you provide some type of input about it or feedback. But this is an older demo model and we just pulled it off of something, but it works perfectly fine. Just got a little bit older firmware in it. So we're going to be giving that away. And yeah, we are going to start a little slower here because I need to catch my breath. Really, we just raced in. We managed to get this set up. I think we got it where you can hopefully see most of it. It's not going to be as good of a view because the camera's a little further away and there's just no way to really move this stuff in. Sunil, very nice to see you. Hi to you. All right, Michael, everything looks good?
Yeah, everything's
All right,
good.
we're going to wait until 12 to start this. So does anybody have any questions in the chat? Or yeah, feel free now to say hi in the chat. Yeah, okay. Hey, Scott from Texas. Glad you could get on. Yeah. And just, yeah, put any questions you have. I did say 12, so, and I just sent out a notice, and I think Michael just made it where you get a notification on YouTube. So I want to give everybody a little bit of time to get back on. A little bit about what we will be talking about. Hey, Jack. Good to see you. Hey, C. Butler from Colorado. Oh, my goodness. Jeff wants Modbus. I do. Actually, I have Modbus videos coming up. I've roughed them out. I did try them. Actually, I recorded them one time. I didn't quite like the view. It was a little, my drive was a little too far away, but I am doing Modbus over Ethernet and Modbus over serial. Hey, Reeks from Fiji. Very nice to see you. But yeah, so we do have some Modbus videos coming up. And Jeff, you know more about Modbus than I do. But yeah, we're going to talk about when your data doesn't, when it looks like it's garbled, how to figure out whether you need to swap bytes or swap words or all those things. Gotcha. Yeah, well, I've worked on Modicon one time. I mean, and it was very robust. But yeah, I don't want to work on Modbus again. Also, I apologize, but everything's in the wrong place. I'm looking over here, but my camera is actually up here for no good reason, except for, yeah, that's where you could see this, and this is what we really want to be to see. Matthew, change the baud rate. Are you talking about Modbus now? Or, yeah, what horribly can happen when you change it? Yeah, Jack, I've worked with some ProSoft cards. They can do some amazing things, but, yeah, they can be a bear to configure. Mainly, I worked with... we had some Profibus networks that we needed to take from an S7400 controller and move over to ControlLogix. And so the ProSoft modules were the best way to do that. And once you get them going, they're bulletproof. But I think they could work a little on the configuration of that. Yeah, but figuring out baud rates and parities and all those fun things are really... a bear. That wouldn't be a bad video. That's one thing I think RS Links does an awesome job at is that auto configure button. And I think everything needs an auto configure button really. Yeah, Scott. Yeah, I am gonna sit here and catch my breath. That's another reason I'm gonna wait until 12. Let everybody else get back on, and yeah, just give me a chance to catch my breath because yeah, we just ran all this stuff in there. But hey, Dean, glad you like automation. So we're going to learn, yeah, because we're going to learn hopefully a lot today about analog signals, which is probably and Jeff Kuiper, you can jump in here on this because I consider Jeff Kuiper a very competent competitor, I guess we could call him. We're great friends. He built outstanding equipment, but even him, if he gets an analog application, he'll ask, like, hey, I want to make sure I'm doing this right. I think analog's one of those that just trips us up. And actually, I'm going to start all over. I know I winged a little bit of a 2-wire versus 4-wire thing there, but we're going to go through it again. And let's see. Hello, Tim. Have you tried software integration with other vendors, PLC or Point IO to compact logics? Yeah. I've done that over Ethernet IP, and actually I've done that with some other networks. So yeah, I've done some of that. I haven't done any videos on it. That wouldn't be a bad thing either. I have a really cool, I got nothing to point at, but if you notice, I have a Yamaha robot that we're getting ready to play with, and that's one, we're getting ready to integrate it with a compact logics, and it is insanely easy. Like, I was going to do a lot of prep work on that because I really was like, oh, this is a robot, it's going to be real intimidating. But then I played with it a few hours, and I'm like, man, I think I'm going to just do this one and walk through it with you. So we're getting ready to do some robot videos and show how to integrate it with the compact logics. And yeah, those guys at Yamaha just made that really easy. Oh, yeah. Yeah, well, yeah. Yeah, reset. Yeah, that's the first thing everyone wants to do is reboot. That can help sometimes, but a lot of times it doesn't. Yes, and I'll holler at him. Chris Elston's who Jeff's talking about. He is insanely smart at this, and what I love about Chris and why I really just think this robot is the thing, and it's going to be a great series, is he is a PLC programmer. So this thing is written by a PLC programmer for PLC programmers. So it's not, not writing a lot of coordinates, not doing a lot of math. He has made some AOIs that make that thing insanely easy. So that is going to be really good. All right, we're going to give it a couple more minutes here to get going so everybody can get back on. And Michael, how are all the frame things and all those things here compared to the training center? Are we better here or worse here?
I will not say. Oh,
apparently we are worse. So yeah, we're getting real creative here, and yeah, we're just gonna wing all this. All right. So Neil, sorry if I'm pronouncing your name wrong. I am going to do some 232 videos about the Micro 850. I don't think I have any good hardware for 485 videos. It's probably the biggest thing. Gene, hello to you. Nice to see you from Peru. All right, you got the spreadsheet things open and all that stuff?
Yeah.
Okay. Yep. We're looking good. You got all that going. Oh boy. Got all types of crazy things going on there. Just trying to get all my tabs straight now. I guess I don't need to know what the power company's doing now, so I can close all this back out. See if I can get all my tabs reorganized here. And I have 3 screens, just as I did before, but now they're actually swapped, so I have to look the opposite way on everything. So we'll just see how everything goes. High impedance. Oh, do we have a delay? Do we have a bad delay? Is that what you're saying, Coaster BP? Well, we're doing the best we can, and yeah, we pulled this off. And really, by the time we ran in here, when we pulled up, I think we were back live in 7 minutes. So by the time we set all the equipment up and managed to get power to it and everything else, so we're all doing the best we can now. All right, well, we are I think we are good here. Michael, how do you feel? Feel like think you got everything ready?
Yeah.
Okay, so first let's just talk really quickly about what the difference between discrete and analog are. And so when you think discrete, that is like something that is on or off only, or a 1 or a 0. So this push button here, we push it and it's going to be on. We let off of it's going to be off. Or if it was a normally closed button, it's on, and we push it, it's off. But it's binary. It's a 1 or a 0. It can be no in between. And same with these lights here. You know, if I switch, we'll just switch it over to that. With this light here, it is on or off. Or, you know, if we open, let's see, we just open a valve so you can see some movement. This right here, this is either on or off. So those are discrete inputs. Compared to binary, man, okay, and the camera angle just isn't that good. So, but right here we have a potentiometer. And so I can switch that. And so we can see now the ball's kind of up this high, and if I turn it a little bit, it's going to speed up and it's going to go a little higher. Or I can turn it back down and it's going to go a little lower. So this is analog. So just like the dimmer switch, you know, on an old school radio, or, you know, a light switch dimmer, you know, you can turn it and you can vary it. So that is an analog signal. And so we can take analog signals either by reading the height of this ball and by controlling that fan output, and we can, instead of this ball being just wide open or off, we can make it do different things. And I think I got enough angle there. Yeah, it's gonna be like, I think the ball is probably gonna disappear, but so we can take and start this, and it's gonna use a PID now. Oops. Switch that. And it's going to control the ball at a specific position. So it's going to get feedback and try to attain it by adjusting the speed of the drive. So and you'd use a PID for that. And let me just drop a link, because we do have a PID series going, just in case somebody's curious. Let me just see here. Man, my chat's not labeled now, Michael, I can't find. Everything's in the wrong place. But okay, so here is a PID series if anybody is curious. All right, let me just catch up here. Yeah, all right. So we are gonna do how to change 4 to 20 to 0 to 10. All right, so I think what you're saying there is you have a 4 to 20 milliamp input, or I'm sorry, sensor, and you only have a 0 to 10 volt PLC input. And what you would use for that is a load resistor. And let me see if really quickly I can find you a link to that, because I did a video on that. Log right here is talking about how you can put a 250 ohm resistor across your PLC, your 0 to 10 volt input, and read a 4 to 20. So read a 4 to 20 sensor with a 0 to 10 PLC input. And yeah, sorry guys, when I get frazzled, I have to talk to type. So you're going to hear me talking everything that we're typing. But okay, so yeah, that would be that. Hello, Kevin. Glad you could get on. And okay, Sean, I probably won't get into calibration in this one. That's something we could touch on. I gotta be honest, I don't do calibration. You know, we put it out and maybe somebody else calibrates it, but usually we're doing more troubleshooting. So we're doing more of simulation. Actually, we're gonna do some simulation today. And I do draw a line there. In other words, I will simulate a 4 to 20 milliamp signal. But calibration, there's a lot of I's that need to be dotted and T's crossed for calibration. And so I don't know if I'll touch on that or not. And yeah, well, we do have a VFD series, and I'll drop that in a little bit. Let's see, 4 to 20 question. I know it's normal 24 volt, but I saw a sensor that outputs 4 to 20 at 10 volt. I know, Compact Logic's 4 to 20 is a 4 to 20, as long as it can push it across the resistor. And we'll probably hit on that a little later. You know, and okay, you know, that's one thing I figured it would come up a little later, but we'll go ahead and say, I'm not going to discuss heart in this video. And honestly, there's no, I mean, you know, we all end up in our narrow niches. And mine just happens to be that I don't work with heart much. I've worked with heart one time in the last, like, I guess I did my first analog application like, I don't know, 20, 25 years ago. I've ran into one heart application. Just the lane I run in, I don't get into a lot of heart. Heart is very popular in certain industries, just not mine. Okay, but let's go ahead and see if we can get started here. I did not even try switching screens, so let's figure out what happens when I try to switch screens. Look at there. We've got RS Logics. That's looking good. So we're going to start with let me get the trainer up here because I wanted to show you that just so we could see on and off. And yeah, we had all this nicely planned, but we are just going to kind of move things around as needed. Good grief, I'm glad we grabbed the right trainer and all that franticness because there was two of them sitting side by side, Michael. Okay, but yeah, so we are going to be using a Compact Logix 1769 L16ER B1BB, and it has 4 analog modules on it. I went ahead and set this up with all, just in case some questions came up. So we have a 0 to 10 volt input module, a 0 to 10 volt output module, a 4 to 20 input module, and a 4 to 20 output module. So the first thing I'm going to do is I'm going to create a program with all that in there. So I am going to select our 1769 L16ER B1 or BB1B, and I'm just going to call this our MA stream. And then the most important thing on these L16s is you got to make sure that you put your expansion IO modules, and that's the number of modules we have over here to the right, and that is going to be 4 modules. And so we're going to get that started. Yeah, and Gordon's giving some good information there, yeah. Because I was like the dampening parameter, that sounds like something specific to a certain instrument. I know heart is very good for, you know, calibrating things that are horribly in the wrong places to get to. And that's about the extent of my heart knowledge. I can get some good diagnostics info. Okay. But all right, so we are going to, oops, we're still getting there. All right, first thing I'm going to do is I'm going to configure these expansion modules. So right here, the expansion IO, I have 4 modules. I'm going to add all of those. So new module. And one thing I do love is the search feature up here because there's, you know, a gazillion modules you could do. And right at the bottom of the 1734 modules, it tells you what they are. So this is 1734 IE2V. And so I'm just going to type IE2V. And it's going to be the only one there. See, that's a 2-channel analog voltage input. And I'm just going to call that voltage input. And then my next module is an OE2V. So we'll put in an OE2V. That's going to be our voltage output. And then the next one is going to be the IE2C. And this is a, well, let me just put it in so you can see exactly what it is. IE2C. And okay, talking about heart. So there is actually a heart version of this module, and that would be really neat. Maybe I will play with heart one day. But, you know, it's just one of the, you know, especially when it comes to custom hardware, you know, we have a very limited budget for that. Usually most of the stuff is stuff we're picking up on jobs as they run through making videos. But all right, we're going to use this IE2C. That's not the heart. And this is the one main one we're going to work with, though. This is going to be our current input. And that means our 4 to 20 milliamp input. And then our final module is going to be an OE2C. So OE2C. And that's our current output. And that's just to start with. We're going to download this program right here. Hey, yeah, this is Studio 5000. And I'm using version 32 of it. This is what you use to configure the control logics and compact logics PLCs. And I'm going to go ahead and download this program. And if we're really lucky, I have everything ready to go on this because, honestly, it's been a while since I did any of this here at the shop. So let's see if any PLCs show up. Getting a lot of red X's, but hopefully, there we go. Look at that. So I'm going to go ahead and just download this program. Yes, we are downloading pretty much a blank program because we're going to find these values and we're going to wire to them. And I'm going to try. Michael, where'd my bank at?
It's on your desk. Right? It was on your desk.
I got it. Hey guys, it's going to be a little messy here because really I just grabbed everything I could really quickly. Alright, and really we're going to put that back in the run mode and hopefully, we're looking good. But okay, so the next thing we've got to do is we've got to figure out how to wire our analog input. And so if we go to the .io digital and analog manual, and I like this one because it has most of the modules. It doesn't have all the modules, but in this case, I can hit Control F, and I'm going to be looking for IE2C. And if we go down a little bit, right there, there is the wiring diagram for it. So I'm going to click there, and this is going to give us the user manual's wiring diagram. And here is where the problem really starts with using 4-20s. Is if you look, we have two different wiring diagrams. Oh, my mouse is smaller on this computer, but okay, I'll just use highlights. So this one, on this side, you see that we have an input, and okay, we have a chassis ground, and then we have a voltage, or a V terminal, which we can assume is voltage actually right here. V is 12 or 24 volt supply. And then we're going back to the input. But on this side, see that we are getting an input, same as we were, and we have a chassis ground. But in this case, we're connecting to the common. So right away, people look at this and they're like, I have no idea what to do because one of these says connect voltage and an analog input, and the other says connect our common and analog input. Well, if you look right here, this is a 4-wire and this is a 2-wire. And so in the 4-wires case, you see they kind of show 2 more wires going over here and then they say AC or DC. It's still not super clear, but right here, which let's see if I can smoothly do all these things. You have no idea how hard this is. Yeah, everything is backwards now. We'll figure out how ambidextrous I really am. So this is a 4-wire setup right here. And so we have our power supply. And it could be 24 volt, it could be 12 volt. This could actually be 480 volt on a drive even. But mainly it's going to be some external power supply that is really not in any way related to our milliamp circuit. And in this case, the analog signal, what this device is going to do is it's just going to regulate the current coming through. So we're going to connect plus to the analog plus, or usually sometimes it'll say MA plus or milliamp plus, and then analog minus is going to go to the minus, or in our case, the common. And that's what you're seeing here on this left side. So we have an input or analog input. We have 1 wire, and it doesn't even distinguish here. I wish they would be a little more specific, but it can actually be confusing. I can see why they don't. Is this wire right here is the plus on a 4-wire system. Now note that on a 4-wire system, this is a plus wire because that's going to matter in a second. And then the minus wire is going to be this common. And then, yeah, we do have a shield wire or a chassis ground. And depending on your device, it may not have this. I kind of wish they would dash that out, or even, I know you can't really say optional there, but really a lot of times there's only 2 wires. But anyway, on this side, this is a current 2-wire device. Now, one thing I did miss saying on this is this right here is what we call an actively powered device. So this is actively powered from somewhere else. Also, you have a 3-wire device, and on a 3-wire device, well, my marking isn't working. On a 3-wire device, the analog minus and the power supply minus will be internally jumpered. So a 3-wire device will be wired typically like a 4-wire device. Yes, John, you're right. That well, it's Studio. Yeah, I did say Studio 5000. RS Logix 5000 is the older version of it. I think Jeff Kuiper, if you're still on, you can probably tell me exactly. I think, what was it, version 2022? They changed the name from RS Logix 5000 to Studio 5000, or Studio 5000 Logic Spew Designer or something. I can't even think of the full name of it. But okay, this is a 4-wire device, and now let's look at a 2-wire device though, because this is where the confusion really starts to come in. Whoops, wrong one. Let me get to the right one here. And so this is a 2-wire device. And so same deal, we have an analog plus and a minus, or 2 wires mainly, on our sensor. And we're going to send 24 volt from our power supply plus to the plus of the sensor. And here's where it gets confusing to people, is we're going to take the minus of that sensor and we're going to go to the plus, or our analog input. And then we're going to take the minus, or the common, and we're going to go back to our power supply. And this is what we call passively powered. So this thing doesn't actually get power. And it really confuses a lot of people, because they're like, well, I mean, where is it actually getting it? Well, it's going to consume a little bit of power out of this 4 to 20 milliamp signal to power it. And here is where understanding that current and power are 2 different things comes into play. And I had some neat things to show that, but and unless somebody asks, I'm probably not going to go try to hunt for those now. But yeah, okay, Jeff says he thinks it was version 24. But around version 24, they changed the name of RS Logix 5000 to Studio 5000. And Michael says, I need to take a moment to drink some water so that I can stay calm, and remind you to hit the like video on this live stream and to subscribe to our channel. We put out at least 1 automation video a week, and yeah, we usually put out a live stream about once a month. Yeah. But okay, so we need to figure out whether we're going to use a 2-wire or a 4-wire device first, and we're actually going to wire both of them here. So I'm going to go back, if I can get there. There we are. So the first thing we're actually going to do is we're going to wire a 4-wire device. And so that means our analog input is going to go to one of the wires, and then we need the common, or terminal 4, to go to the other. Now I got to be honest, I don't actually wire this way, and probably someone will disagree with me or tell me, hey, you're being overcautious for nothing. Is this goes through the back plane, but ends up being the same 24 volt that you're powering this with. In this case, I usually hook this directly to the 0 volt of the power supply. And I'm going to show you both ways, just so we can see that it works. And so we're going to look at our analog simulator here now. And on it, if we go, good grief, it's a long stretch to get up here. If we go to current source, because a 4-wire device is going to be a current source. Oh man, even my video is backwards here. So yeah, this is a real struggle. Then at the bottom, you're going to see that the red terminals are PLC input, and the black terminal is the common. Hold on, just a second. I got to go away from now on. I said we're improvising. But okay, so the red wires are PLC input and the black wires are common. So I am going to turn the power off to the trainer, and I'm going to grab a couple wires and hook them to the analog simulator. And then if we go back to our manual, we said that our PLC input is going to be that top left terminal. And the third one down is going to be our common. And if I had not ran out so fast, I had a terminal to show you. But in this case, you're just going to take my word for it because, yeah, you're going to struggle probably to see that. And in this case, the camera does not mount well. Michael, I need a terminal block screwdriver. You want to grab me one? A terminal block screwdriver. You want to grab me one? I asked for a terminal block screwdriver. He hands me a Phillips screwdriver. Come on, bud.
Stop. I've been here for a while.
Yeah, he hadn't been here in a day. He forgot where all the tools were. But okay, so that top left one there, that's going to be our input. And then the third one down is going to be our common. We'll power this back up. Wait for the PLC to power back up. And now is where I would usually tell you to make sure you subscribe and like our channel. And yeah, make sure that you throw any questions in the chat because remember, we're giving away an analog simulator to someone in the chat. So you can't say hi, but you can ask a question or put some input in about our analog inputs. All right, we're waiting for it to do its dance here. Not you to do your dance. All right, we're back on. So let's go back online here. Okay, why you're not showing up? You're not showing up just because I'm live streaming this. There it is. Yeah, I was probably just slightly impatient. We're going to go online. Okay, now the next thing we got to do is figure out where is this analog input. So I added them in these expansion modules here. And if you notice that there is a number in front of these expansions. So our embedded is 1. And that means that's local :1. So our first module is going to be 2. Our second module is going to be 3, and our fourth module is going to be 4. So we need to go to local 4. Input, and we are looking at this channel data right here. And so now I'm going to run, well, let me turn off the power saver of this. Just so, because I ran out without the analog simulator that we were using, so we had to grab one really fast. So sleep timer, we're going to turn off, and our LCD timer, we are going to turn off this so we can keep this as bright as possible. All right, that looks much better. Oops. Okay, and now we'll find out who was actually paying attention because I said here put these on the first slot, but that's not right. This is the voltage input. Let's see. Will you have drawings on your website so we can watch and reference them? Well, no, you pay attention, Jeff. But actually, I do have this in a lesson, and I will try to find that lesson here in a little bit. Maybe while we're waiting on this compact logics to power up one of the times. And it goes through the pluses and minuses. Alright, so now I have it hooked to the right place. I should have shown you that. One of the neat features of the analog simulator, and the reason I knew that something was wrong, was with this off, you see this open wire banner, and I apologize, especially now, my wires are short and my camera is in the wrong position, but it says open wire right here. And that told me that something was wrong with my analog circuit. And that's one of the best features about this. So if I hooked a wire back up, or in that case, I just had it hooked to the wrong style of input, then it's going to show something here. And now we can go in to Studio 5000, and we can see, all right, I got it at 1 milliamp right now, and we're seeing a crazy value here, 816. But this is a 4 to 20 milliamp signal. So let's bring it up to 4. Whoops, went too far. And at 4 milliamps, it's showing right at 3270. And if we go up to 20 milliamps, then we are showing 16,378. And so these are the rough values of this. So we're at 20 milliamps now, and yeah, we're seeing 16,378. And that doesn't, you know, I see this all the time. One, I will see people that will put those values in. They'll use the raw values and they'll figure out, well, I need to kick a pump on at like 12,000 raw value. Well, no, we don't need to do that. We need to figure out some scaling. You know, we need to do some math. And yeah, thanks, John. This is a slick little simulator. I probably ought to put a link to this while we're here. Let me just pop that link in. But we need to do some math here. We've got to, you know, we can't really guess. And even then, what is this 16,000 number here is the next thing that we need to figure out. So I'm going to drop a link here to the analog simulator. This is the PLC Tools Sim ALP2, and there is a link to it. Yeah, we can simulate a 0 to 10 volt, and like I said, I did set this up. Let me just pop a wire off of here so that I can show you. Yeah, so if we just go to the main menu here, then yeah, oh, I'm sorry guys, my wires are like a little short, but yeah, we have a 2-wire which we're getting ready to use. A current source, a current 2-wire. We have a current source, then we have a voltage source, and yeah, the voltage source will do what you're asking for there. But okay, so now let's talk about how we can figure out exactly what this is. Actually, even before they do that, let's talk about 2-wire, because realistically, you're going to see way more 2-wire devices than you are 4-wire devices, and they're going to give you the most trouble. And it's not that they're not, how should I put this? It's not that they're fragile. They're more confusing, and also they are put in much worse locations, I guess is the thing I can put. Usually you got a nice transmitter for a 4-wire signal, and usually it'll be, you know, have some numerating. You know, you got a level sensor drop down in some sludge pit. It's going to be a 2-wire device. So they just end up in grimy, harsh locations. Sean, glad you have one of these. Yeah, this is one of the devices that I almost never leave without. What is the make? That is PLC Tools. That is the make of it. So the model is a Sim ALP2 and it's analog simulator. And right above you there, I've got a link to it. Okay, but let's talk about 2-wires. So if we go back to our manual here, this was our 4-wire side. And first, you know, in here, I'm not super happy with how they do this manual, but you know, everybody is a critic, so I don't want to go too far down that. I do have people that think that 2-wire devices are for input 1 and 4-wire devices are for input 0. That's not true. You can use these on either side. But let's look at the 2-wire device. So in this case, we need to send voltage to it, and then we need our analog input. So we're going to do the exact opposite of what we have. Now, one thing I didn't show is, yeah, now whether it's just me being kind of cautious or just being in usually horrific power environments, that's kind of coincidental since we just had a tree catch on fire right by the training center. But I usually would not put the common, or in the 2-wires case, the voltage through the module. And my thinking on that is, if you do have something, you cut your risk in half, especially on the voltage side. And we go out and we power something and we short the conduit, well, all that current's going to have to go through here. And I get they have protection and all those things, but I usually would feed it from the plus 24. And usually I'm going to have a fuse on it. So I'm usually going to have a 32 amp fuse. I'm sorry, not 32 amps. 32 milliamp fuse on my milliamp signals. That way if something does happen, pops the fuse, everything else gets to running, And the first thing I can tell a technician when he's like, hey, my level sensor isn't working, I'd be like, hey, check the fuse. And, of course, first thing you do, what do? You change the fuse again, it pops again, and you find out that your device is bad. But, okay, in this case, what we're going to do is, first thing I'm going to do is I want to move this comment. And let me go over here to our screen focus. And let's go to, you see right now it's 16,380 roughly. Is I'm going to take this common off of here, and I'm going to move it over to the 0 volts on my power supply. Just so you can see, it's the same value. So that's how I would actually wire it. So I'd only end up with one wire over here on the analog signal. Also, I think that makes it a little clearer when we go to troubleshoot. When you have two wires coming out of a device that is foreign to you, or you're like, yeah, I have no idea about 4 to 20s. I know how to wire a light switch. When you see two wires coming out of it, it's kind of magical. I mean, if I have 24 volt going to a fuse, going out to a device and coming back, that's almost like any other circuit. So I think it just removes a little bit of it. That's just me though. So now what we're going to do is we are going to make this a 2-wire setup. So if I go back right now, I can go up and there's current 2-wire. And I'm just going to pop one of the wires off of here just so we don't have to deal with any shorts or anything. And when I go to it, we're going to see that our PLC input is still our red, but see, it told us now we need plus 24 here, just like our drawing did. So now this wire needs to go to our plus 24. But first, let me do it exactly like they have it. And so if we go and look at the wiring diagram, they're showing it going out of the bottom terminal. Now, again, I'm using input 0 here, but we're coming out of this voltage terminal here for our 2-wire device. So I am going to take this wire loose and put it on that bottom terminal. What?
It's like I'm oiling up a paper.
We left everything that wasn't essential to do this live stream at the training center, so we are having some interesting things right now. But okay, let's see. Please save the streaming to watch it when we need it. Well, if it turns out okay, we will. Otherwise, we may be doing another live stream. But I think this is going to be okay. So now we have plus voltage. Oops, didn't tighten that side post up enough. So now we have plus voltage coming out of that bottom terminal going to the black. And then our red is going back to our input. So now let's go back over to our screen and let's look at that value. And all right, right now I'm at 0 milliamps, so I'm going to bring it up to 4. All right, so 4, look, we have almost the same value, 3277. That was roughly what we had last time. And we're going to bring it up to 20. And we've got roughly the same thing, 16,384. So at 20 milliamps, we're showing that same value of 16,384. Now again, I would not have this here, especially on the voltage side, because there's too many things I think that can happen in the field. I would have this wire coming out of the plus 24. And again, especially if I'm on a larger system where there's a lot of analog and, one sensor going back and take down, all those, I will have 32 milliamp fuses on them. That way, and really, this is one case, people are like, hey, you shouldn't use fuses, you need circuit breakers. I don't think there's a 32 milliamp circuit breaker out there. So this is one case that you do use fuses. And same deal. I move it over, and we still have 16,384. Now, that's great and everything, but what is the 16,384? That's the next thing we need to figure out. And Rockwell has done so much of a better job. Let's see, hold on, I'm sorry. Jason, yes, you are correct. The first one, and we can look at that right here. The first module is a voltage input. The second module is a voltage output. And then we have the current input that we're working with right now and a current output for a 4 to 20 out. But used to, it was in many of the PLCs. This isn't knocking Rockwell. In many of them, it is a guessing match to figure out what these values are. But if we double click on this module here, it's going to bring up the module properties. And then right here, we have the configuration tab. And if we look at it, here it is. Our low engineering is 3277. And our high engineering is 16383. Now, this is one of those that we need to do a little math on. And I know a lot of times when I start saying math, I get glazed over looks. But really, if we walk through this slowly, then I think we can do it. And hopefully I have enough of what we need down here to walk through this math. Because what we're going to use is what they call y equals mx plus b. And when I say that, everybody's heard of it, and everybody kind of remembers it. But then it's like, all right, I really don't know what it is. So if we look, here it is, y equals mx plus b. And yeah, I'm not even going to put this in the present mode. We're just going to do this like this. And so our y is our scaled value. So in this case, what I want to scale this to is, I'm going to scale it to 4 to 20 milliamps. So I want this to end up being 4 to 20 milliamps. Now, yeah, I know usually you wouldn't make it 4 to 20. Usually it's going to be some real value. But let's start there just so we can understand it. And then we're going to have a slope here, and that's m. And this is going to be the ratio between our scaled value and our raw value. So we're going to figure out, you know, how many units of that 16, whatever, 383 to 3277, or the opposite way. Right here it is. 3277 to 16383 is going to equal this 4 to 20 milliamp signal. So we're going to need to figure that slope out there. And then, man, guys, I'm sorry, I'm really struggling with my screens being backwards. But then we're going to have an offset. And the offset's really important on 4 to 20 because it's by far the most confusing thing when it comes to scaling things. Is we have what's called a live zero. And what that means is 0 is not our 0. 4 is our 0. So we have to account for that. So let's talk first about what is M. Because M, usually everybody can follow pretty good. So it's the milliamp full range divided by the raw full range. And you know, actually I have that backwards. So let me correct that. It is not. Oh yeah, it is. I have something wrong here. Where did it go wrong? Oh, that's wrong. This is wrong. So cut that out. Big grief, I hope that's not wrong to the whole thing. But hey, like I said, everybody keeps saying your videos are scripted. No, they're not. But okay, so that's going to be our full milliamp range divided by this raw range. And okay, where did I get these numbers? Let's make sure we don't get confused here. This 16, 383, and this 3277, that is the range of our engineering units. So our low value, or the 4 milliamp value, is 3277. Our high engineering is 16383. So then, what is B? Well, in the case of this, B is whatever that offset's going to be. And for us, it's going to be 4 right now. Because we're going to scale this to 4 to 20 milliamps. Now, later on, we're going to change it. I don't even know what we're going to change it to now. Let's make it a level. So we're going to change it to a level sensor. And so typically a level sensor, let's say it's a pressure type level sensor, it's going to be 0 to 10 volt, or sorry, 0 to 10 PSI. And in that case, 1 PSI is going to be 2.31 feet. And so 0 to 10 PSI equals 0 to 21.3 feet. And we'll get to that in a little bit. But right now we're just going to use 4 for that B. Now this is the one that confuses most people, is X. And that's because X does not equal your analog input. And that's what everybody always wants to do is, you know, they want to plug in their local :4 : everything after that for our analog input. But it's not, because we have a live 0. And so our 0 in this case is the analog input minus that raw 4 milliamp value. And that means that X is going to equal our analog input minus the 3277, which is our low value. So if we put that all together and, okay, I did it right here. Did I just, yeah, I typed that I did something wrong earlier, but okay, we're right now. We're cooking with gas now. So right here, that means if we put it all together, our Y is still going to be our scaled milliamp value. And that's what we're going for right now. Our slope, or M, is going to be 20 minus 4 divided by 16,383 raw 30 minus 3277. Now I'm leaving these units in here for a reason right now, because while it's a small step, I'm going to show you how you can figure out for sure that you have these numbers the right way. And it's something I still have to do. Okay, now the X is going to be the analog input minus 3277. Now what is the analog input? Well, right here, that's where this is going to come in. Our analog input is that local :4:I channel 0. Let's make sure we see. That is what we found our value going at right here. So that is this right here. Okay, so with all that, that means that Y equals the local :4:I channel 0 minus that 3277 to get rid of that live 0. Now I'm still leaving these raws in here, and there's a reason for that. And then times 20 milliamps minus 4 milliamps divided by 16,383 minus 3277, and then plus 4 because we do have that live 0. Now here's just a little bit of why that is, and really I don't want to get too deep into this because yeah, this is not a math class, but this is how you can kind of keep track of it. And 1 divided by, or any number but divided by itself, is 1. So 1 divided by 1 is 1. In fact, you know, as crazy as it sounds, let's make sure we see that. Let me bring up a calculator here, and just so we see, yeah, 1 divided by 1 obviously equals 1. And if we go and put 2 divided by 2, it's going to equal 1. And if we go 27 divided by 27, it's going to equal 1. So any number divided by itself is going to be 1. Now, what we can do with that is also that means that raw divided by raw is going to be 1. Or, you know, apples divided by apples is going to be 1. Anything divided by itself is going to be 1. So using a little bit of math, first we can get this out of here. And I'm not even, yeah, let's see, let's go ahead and go through this. So mainly we're removing this and getting it down to right here. And this set of values here, this is 4 to 20 milliamp, milliamp and milliamp. And this is raw. Well, then here we're dividing by raw minus raw. So in this case, if we just skip down, raw divided by raw, those two are going to cancel out. And we end up with local :4: input channel 0 minus 32,077. And then just put that times 1 in there just to see that that goes out. And then everything else is milliamps. Now, somebody put it in chat if you really want me to go deeper into this, because I kind of threw this slide in just in case somebody really questioned or really wanted to know why. Hey, Daryl, glad you could make it on. We've had an interesting stream already. I'm glad you found us. But okay, in the end, here's our equation. So local :4:I channel 0 data minus 3277 times 20 minus 4 divided by 13,383 minus 3277 plus 4. That's going to be our 4 to 20 milliamp value. And actually, we'll save that for a little bit. But okay, now that's a lot of numbers, and we did not come here to do math. We came in here to figure out how to do analog inputs. So what can we do with that? Is I'm going to highlight this now, and I'm going to copy it. And we are going to go to our PLC program. John, you could change it, and there are pros and cons to that, because mainly what would you want to change it to would be the question, because you notice that the data type here is an integer, so we are limited in the number. So if I put a 4 and a 20 into these values and just said, hey, I want it to be 4 to 20, then we're not going to get much scaling. So typically, there are some that you could do it that way, but typically I see people doing the scaling outside of them. So what we're going to do is we're going to open up our main routine. And then we could go to our math tab, compute math tab, and we could do a bunch of adds and subtracts. And in a lot of the older ones you could, or you would have to, but we're going to use this compute instruction here. Now notice I copied and pasted that. So now if I highlight this, you get there, man? Michael now feels comfortable with everything, and now he's trying to get his computer plugged in and get a little comfortable himself. But yeah, so I'm just going to paste that equation right into our expression. And then we need a destination. And so I'm going to make this, actually I'm going to show you how to do this in ladder, function block, and structured text. So this is going to be our scaled ladder. All right, and notice we got question marks there. That means that we do have to create this. So I'm going to right click it, or you can hit Control W, and we're going to create a new. And then, oh, actually this would be good to talk about is, all right, it's going to default to a double integer. And yeah, let's, all right, first I'm going to create this as a real. And then I'm going to copy this. Oh, why do I have red X's? Oh, okay. Well, let me hit the verify button so you can see this, because I don't even know what this one will show. Let's drag that up a little bit. And okay, compute invalid number of arguments, and then we got operand zeros, we got balance parentheses, and we got some craziness going on here because all our parentheses look balanced. But what I did is I made this, I was trying to make it easy for you to see in our initial thing. So I put the commas in here. It's not liking those commas, so we got to get those out of there. So I'm just going to go up here and we'll go into that. And we'll take that comma out, and we'll take that comma out. Is that all the commas? Oh, yeah, so now, yeah, our red X is gone. We're looking good. But also, I am going to copy and paste this, and I'm going to make this scaled ladder DINT. Whoops. So I'm going to make a second one of these. So this will be DINT. And I'm just going to create that. And I'm going to leave this as the default. It wanted a DINT. We're going to create a DINT for it. And I'm going to put that into the program. Okay, Matthew. So in the Slick, in RSLogix 500, there was an SCP instruction, scale with parameters. And so in Studio 5000, there isn't. You do use the compute, but stay tuned because in function block, yes, we do have a scale instruction. And so that probably would typically be my preferred way to do it. I always liken these to start off of ladder because most of the people watching are just a little more familiar with ladder. And so I always try to, in the end, in these situations, I try to show multiple ways that we can do it. So we're going to show how, yeah, there's a scale instruction in function blocks works super easy. But you're going to run into this. You're going to see this. And so that's why I like to do this. That way you'll get familiar with, okay, this number right here. Yeah, all right, I get it. But okay, let's see what we got now. So first, we're seeing a value. Look at there. We got 20 milliamps. And we have 20 milliamps in both of them. And yeah, if we look on our screen, yeah, we're showing 20 milliamps here. And if we go and let's drop down, this is where it's going to show a difference. In fact, let me get back to the screen. As I'm going to drop down to 19.9 milliamp. And notice that I dropped to 19.89, which is pretty close, 19.8986 milliamps here. I dropped to 19 here. And if I drop on down, you can see that our real value, it's following it pretty good. I'm just going to bring it down to 19.1. So now you can see on our analog simulator, we're showing 19.1. And right here, we're showing 19.09 something. And yeah, so we're really close, but we're 19 here. Now I'm going to drop it down to 19. And notice that this one went to 18. So what's happening here is a double integer is a whole number. And this is a real, so it can have a decimal. So we're having rounding because we're using the double integer. Now, I was kind of waiting to see if anybody popping in chat, but it doesn't look. Does anybody notice anything strange that at 18.99 we'd be at 18 milliamps? Does that seem like some funny rounding to anybody? See if anybody's actually listening in chat, because remember we're gonna give away. Do what? I know. Michael's over here told me we have a bad latency at the shop, so you got to give everybody 10 seconds. So yeah, we'll take that 10 seconds to say, hey, don't forget, participating in chat today will give you an opportunity to win this Sim ALP2. This is a demo model. It's a little bit older version, but it still has all the same capabilities. But yeah, so we got some truncation, but we got some weird truncation going on, don't we? Because typically you would think it would round. We would get at 19.9, or here's the math, we're going for 18.899 milliamps. You'd think that we would get 19. We'd have the value. And so, yeah, we got a few people that are saying truncation here. This is actually rounding. And, you know, the first time I saw this, I was like, what is going on? Could Rockwell really have forgotten how to round? Because really, yeah, above 18.5, you'd think it would go to 19. But what's happening is we're getting rounding in this compute statement. And I'll show you how to fix this, because sometimes you do need to go to an integer in these cases, or a double integer, if we're shooting across Modbus. Now, typically, even then, I would go to a real first, and then I would go to it. But watch this. So you see right now we're showing a value of 18 here. And mainly, let's make sure you see that. So let me go back here and make sure you see. Mainly, if we go down to 18.5 milliamp, there's where we ought to see it bouncing, we believe, between 18 and 19. But if we go over here, then yeah, we're not. We're a solid 18, and yeah, we're 18.49 here. But okay, yeah. So Jack, yeah, it could be order of operation, but no, this isn't. So what it is Glenn is kind of onto this, is yeah, you notice when I entered this, we put all whole numbers in here. Now watch this thing. So now what I'm going to do is I'm going to go into this, and oh man, my screens are so messed up. I tell you guys, I'm really struggling because all my screens are backwards. But okay, if I go here and I change this to 3277.0, and I change this one to 20.0, and I change this one to 4.0, and I change this one to 16383.0, and I change this one to 3277.0, and finally I change this one to 4.0. This is the exact same equation, and I'm still going to a double integer that cannot handle any decimals. But watch this. You see right now it's showing 18, right? And we have not made any true changes in the values here. Now I'm going to put this in. And okay, it's showing 18 still. So yeah, at first you're like, what? It didn't really make any difference. But watch this. So right now I'm at that 18.5. And also if you look here, we're actually at 18.49. And so our math would round down to 18. So now what I'm going to do is I'm going to go up to 18.5. And the moment I do that, notice this went to 19. So now we are seeing rounding like you would expect. Right now we're at 18.49 and we're showing 18. And we go to 18.59 and we're going to be at 19. So that's just something to be aware of, is that you have to watch out for the decimals. Even if you're going to a whole number and you're like, oh, well, you know, I'm using whole numbers here, so I don't need to put any decimals in. It does make that difference. So that's just something to be real aware of on that. All right, so let's take a moment here. And one, if you will take a moment, hit that like button, subscribe to our channel. And don't forget, we're giving one of these away. So, you know, I get so many emails after these live streams saying, hey, I thought this would be a dumb question. There are no dumb questions. And hey, here's the thing. If you ask the question, you're going to get in the running for a PLC Tools Sim ALP2. I'm going to drink a drink of water here because, yeah, I'm getting tongue twisted. Michael, how are we looking over there? And I will take a moment because, you know, I did say in the initial stream because we were trying to fill it and hopefully the power would come back on. But really, we could not do these live streams without Michael. You know, everybody's like, will you start doing live streams so, you know, we can, you know, kind of have a little more immediate question response. And I'm like, man, I don't know how to do a live stream. He figured out how to do all this. He figured out how to make it where I could change screens and I could pop over to this and I could do all these things. And, you know, I couldn't do this without him. And this is actually his last live stream. He's going back to school. So the summer is over and Amber will be taking over. So he is diligently training her. And so it should be interesting. We should have some good entertainment with Amber. Probably a little more commentary than Michael. Michael's a little quiet over there.
You don't allow me to speak.
I allow you to speak. Sometimes. Let's see. Jack, I work in data acquisition. Use your use device as 2-wire source. Not quite understand that, Jack. It's going to depend on the specific device, and so in this case, you know, this can simulate a 2-wire or a 4-wire device, but it's going to be very dependent on the exact device that you are integrating with on the data acquisition. There you go, Michael. Yeah, you're not allowed to speak. Everybody who's ever been on one of these live streams know that you have quite an opinion sometimes. But okay, so we now have some scaled values here. And, hold on, let me go back over here. That's all right. The next thing we need to talk about probably is what happens if we have trouble. In other words, what if, like even now, let's say we're looking at these values right here. We see that one of these is 18.5, and we see that one of these is 19. And we're like, I don't know which one's right. And we want to measure it. Measuring a 4 to 20 milliamp signal may be one of the most difficult things that you have to do if you're not familiar with it. Because first of all, people want to go and they want to get a current meter. And we had a current meter sitting right there at the training facility to show you. But you know, they have the clamp meters and you stick them around a wire. Those do not work for measuring milliamps. They work for measuring big amps. So if we had a motor and we wanted to, you know, its full load amps was 12.3 and we wanted to check it, we would use a clamp meter to do that. Aside from some of the high-end flukes, they do have one, and you can tell it's a small little clamp, smaller than my pinky finger, or probably about the size of a pen. Those are clamps for milliamp signals. They're expensive, and they're actually unnecessary because we can do that with a typical, sure I got the right meter, with a typical $10 meter, as long as we can break the loop. So now we want to check the loop. So if we go, and man, the screen lighting just isn't, yeah, our camera is just not as good on this. And hold on, let me see if I can find a picture of this really fast so I can explain. Yeah, the lighting, everything is better down at the PLC lab. It's just set up for that. And honestly, we set up, you know, everybody used to complain about the lighting here, but you got to remember, we're usually building control panels. We just cleared this whole place out really fast so we can move this down here. But if we go and look, okay, and actually, yeah, we're going to get real cheesy here. Here's a video I did that had the meter in it. And so we're going to zoom in on that. There, if you want to know how to use a milliamp meter, here's, oops. Here is how you can, there we go. There we go. There we got a picture of this meter. And this is going to be your typical meter that you see. And over on this side, you see that we have these, oh, you don't see anything I'm doing. Michael, are you paying attention to the chat or are you playing with your phone right now? Okay,
I'm
so.
paying attention to chat.
You are?
Yeah, only chat.
Only chat, okay.
Sometimes you.
All right, well, there we go. Let's see, John, the rounding down seems like a bug that needs to be fixed. No, so, the first time I saw that, really, I worked through it, and I'm like, why is it doing that? But if you work that on a calculator and round up and down like you're supposed to without decimals, you'll come up with the exact same answer they do. So they're rounding right. It's just a matter of without those decimal points, you specify a double integer on those numbers. So that's what's going on there. But okay, right here is a typical meter. Let me get over here. So yeah, oh, and since that popped up, yeah, don't forget to subscribe to our channel. Can't get it to stay there, but yeah, hit that subscribe button, like our channel. We put out at least one automation video a week. And this is a typical meter right here. So on this side, you see that we have a V signal, and then we have a line and a dash line underneath it. And this is going to be DC volts. And then over here, we have a V, and then we have a squiggly line, or a sine wave. And that's going to be AC volts. And DC stands for direct current. AC stands for AC current. So this would be the 24 volts. And that is typically on our trainer. And then this would be, you know, our wall power, our motor power, things like that. But okay, and then over here we have ohms. And those are the ones that most people are familiar with. They can handle, really, we'll call it, they can handle, you know, the, you know, 200 degrees of the meter. And then they ignore most of this other stuff over here. Because we got this transistor thing that honestly, I would have to pull the manual out and figure out myself. But yeah, we can check transistors, we can check PNP, NPN, and I have no idea how to do it without a manual. But then we have this amp side here. And the amps right here, first we have microamps, that's what that U thing is. And then we have 2 milliamps, we have 20 milliamps, and we have 200 milliamps. And then unfortunately in this picture, it's not going to show the bottom here. So let me switch to this, and hopefully it'll come in clear enough. As then, if I pop my leads off here, we have 3 leads on this meter. But we have 3. Man, that is just horrible, guys. Oh, there we go. I can get a little glare on it. That's close. Sorry about the lighting and everything. But we have 3 posts on this. And so we have our common. And then this one says volts, ohms, and milliamps. And then this one says 10 amps. So first is, where do your leads need to go? And this is different depending on your meter. So in this case, we still want to measure milliamps. Oh no, I hate the A, Glenn. Well, you need to use your you need to use your meter more often, or your analog simulator more often. But you're right. Yeah, that would be bad if your batteries start to leak. So yeah, you probably ought to take those out. But okay, so we need to go to volts, ohms, milliamps here. And then in this case, this one needs to go to common. Now here's the trick to measuring a milliamp signal. And this actually goes for our 4-wire and for our 2-wire, is if we go and look at how we measure one. Is this right here is how we're, so this minus this right here, this is what we had before. Let me pop back over so we can just see. This was our basic 2-wire. Oops, popped to the exact same one. Where'd it go? Oh, get over here. My screens are backwards, man. Everything left needs to go right. Everything right needs to go left. But okay, so this is our typical 2-wire setup that we just made. Is now we want to measure this. Is what I see a lot of people do is they're going to put the plus here and they're going to put the minus here and try to measure this. And there are a lot of pitfalls to doing that. We'll talk more about that in a second. I'm sorry, they would actually do it here. They want to measure this milliamp signal. They're going to put their plus or their black lead here, and their minus or their plus or their red lead here, and their black or their minus lead here. And that's not how you measure a current signal. And that's what you got to think about is, what are you measuring? If we're measuring voltage, that's what we do. We would check between the points that we want to see the potential voltage of. But in this case, we want to measure the current that's moving through this wire. And in that case, we're going to need to break this somewhere. And so to do that, and unfortunately I don't have the right, I had all this printed out and we left it at the PLC lab, but this is almost it, is we're going to need a second analog input, and we're just going to cut right into it. So right now we have that sensor, which is our analog simulator, and we're going to put it to the red terminal of our meter, which is the plus of it. And then the minus, we're going to put to the plus of our next one. So we're looking here, is I have our 24 volts. No matter what you do, wires always end up tangling. There we go. So we have the plus 24 volt going to the black terminal here. And then right now, this one is going to our PLC input. So what I'm going to do is I'm going to, well, first I'm going to put my meter on milliamp. And we are going to take this wire is actually, we're going to connect to the red terminal of our meter. Now I'm going to get the black post here, and I'm going to connect it back to our meter. Which one? Let me make sure you see that. Every time we take a wire loose, we get, and I'm sorry, this is not zooming well, but we get this open wire banner here. And that means the ALP2 knows that something is wrong in this circuit. And that's one of the best troubleshooting tools about it. So now I'm going to put that back into there. Let's see. Wires untangled. Oops. Okay, so we're going to have a lesson in a second because we have meter X. That's for just a second. I grabbed the wrong meter. So let me pop this back out. And let's grab the non-X meter. And we're going to do the same thing. So our red wire is going to end up on our red post, and our black wire is going to go to there. So now, put this one to 20 milliamps. And one, just so you can see, so the moment, yeah, need like 10 hands for this, but the moment that I touch this wire to complete our circuit, that open wire message goes away. So that moment it knows, okay, we're ready to go. But okay, now I can see that my signal says 18.51 amps. And I think the backlight does not work out. Oops, backlight. There we go. So you can see right there is 18.55 milliamps. Now again, you got to remember this is a $10 meter. But if we go and look, that should be pretty close. And yeah, we're at 18.59 milliamps. So when you want to measure a signal, then you're going to want to take the loop loose and put your meter in between it. Now here is the issue, and this happens, and here is what the X meter is for. Is I'm going to take this back off, and we're just going to substitute meters because I get tired of changing fuses and meters to show this as an example. Is now as I'm going to do, I'm going to put this one back exactly where it was, and let's say, oh man, I think that's not the problem. And now I want to check voltage. And so without thinking, I go over here and I'm going to check 24 volts. So I'm going to put my black lead on the plus. I'm sorry, my red lead on the plus, my black lead on the minus. And I'm like, oh, well, why don't I have any power? And I'm like, my PLC's powered up. And then I look and I'm like, oh man, I forgot that I need to change the voltage. So I switch it to voltage. And now I test it, and it reads fine. But the moment that I touch the plus and minus to this on milliamp, I blow the fuse in this meter. And what I've done, and I keep this set up just for this, is inside this meter for that milliamp signal, there's a little 5 millimeter by 20 millimeter fuse. And if we look at it, it says that it has a 500, you're not going to be able to see it. Will it show up on that screen capture? Let me go up here because I'd love for you to see this. This is important. Yeah, so right here, oops, there we go. You can see that it says, it's a little fuzzy, but this says 500 milliamp max fused. Also notice this one over here is unfused. So you're going to blow the meter if you're on this one and you go over 10 amps. But so 500 milliamps. Well, my power supply is capable of putting out 2.5 amps. So the moment that I check that, it's going to blow the fuse in our meter. And this is one of the most difficult things to get people to understand is I just showed you. Yeah, now I can check voltage. We got 23 volts. And I can also check amps. works perfectly. But it is not going to work on this milliamp scale. And everything else will work perfect. So the next thing people do is they're like, they go in, let me plug this back in. So they got the wire right, and they are sure they have this thing wired right. And put that back on milliamp. And they touch it. If I got enough hands here. And yeah, we're showing almost perfect 0 on our milliamp. And yeah, this is saying 18.6, and it's showing up in open wire. And you know, they call me and they're like, hey, something's wrong with my simulator. It's showing open wire. And we go through the schematic, and their schematic's perfect. And I'm like, check the fuse in your meter. And well, actually, here's a funny side note. Is, you know, if somebody has this $10 meter here, and I tell them, hey, your fuse is blown in your meter, they're like, okay, let me run down the hardware store and grab another one. You're probably right. Somebody has a fluke meter. Those are the ones that always get me. Is they're like, I have a fluke meter, and it has a $38 fuse in it. I've read the manual front to back. I know how this thing works. And I'm like, I'm glad you've read the manual. Go to the page that tells you how to change the fuse and change it. You've blown the fuse in your meter. And yeah, $10 meter people, they're like, yeah, I probably did. You know, you got a fluke. And I promise you, the fuses blow just as fast in a fluke, because, you know, fluke is they're gonna protect their equipment. So it'll blow those fuses, those $38 fuses, as fast as it'll blow the 50-cent fuses. Now, here's how you can check your meter. And I don't know why it took me like 10 years to think of this. And I don't know why no meter manufacturer does this. But okay, so I have this one on 20 milliamps. Now we know that the fuse is blown now. And just like we would typically check a fuse, we'd use ohms. Well, if I have this one on milliamps, and I take my other meter, and I'm going to put it on ohms. And unfortunately, this one I think I grabbed. Oh, nope, it beeps too. Now I'm going to touch. Said I need a ton of hands for this one. But now I am going to touch these, and we see it's open. So you can take a second meter and ohm out the one that you think is bad. Because now I'm going to do the opposite. I'm going to switch this to 20 milliamp, just like we want to measure, and I'm going to ohm it with this one. So now same thing, if I can get this juggling act down. Shove that up there, because this is the one we're concerned with. Because remember, our bad meter will measure ohms. I touched 2 leads. Good grief, now. I touched 2 leads there. I touched the other 2 leads here. And this one's good. So there's how you measure whether your fuse is blown in your meter without having to take the cover off of it. But there, okay, so there's a little bit about how to measure a milliamp signal if it's bad. Let me put this back just like it was, because now, yeah, let's talk about, you know, we got this thing scaled. What can we do with it? So plug that back in there, and let's check and make sure this still works. So we're showing 18.6, and mainly we're not showing our open wire banner now. And if we go here, then yeah, we're showing 18.59. So we're looking good here. Okay, let me catch up a little bit on chat here. So, let's see. Yeah, Jack, you're right. You know, and it did. It took me forever to think of that. I had no idea why. It was like so obvious once I thought of it. And yeah, I couldn't, I just couldn't come up with it before that. Let's see, another problem, John, another problem I've caused this. Yeah, and that's something we talked about at the beginning of this, is you've got to know whether you need a 4-wire or a 2-wire. And, you know, the manuals are not super clear on that. You know, when we go pop back to this manual here, I mean, this is really difficult. I mean, if you're not familiar with analog signals and you're like, hey, I bought an analog 4 to 20 milliamp sensor. First of all, you do not specify when you're purchasing one whether it's 2-wire or 4-wire. It's something you figure out later. And so, I mean, there are a lot of hoops to jump through that really are difficult when you haven't first done it. But okay, now that we have that and we figured out a little bit how to measure it, we need to do some programming with it. And okay, we've got a PID series, and I don't think I want to go there today. what I want to do is, what I find a lot of people, first thing when they do analog is they're like, okay, if I have discrete inputs, I have to use discrete outputs. If I have analog inputs, I have to use analog outputs. That's not true. I mean, analog input's going to read something. It's not in any way linked to something outside, so we can use an analog input to make decisions to control discrete outputs or on-off outputs, and we can use discrete inputs to control analog outputs. And I think I have a video on that. If anybody's interested in that, let me know. I will find a link to it. But okay, so now we need to do something and do some programming. And so we are going to use, well, since I left half of our setup down at the training center, we need an indicator. And yeah, we're going to turn this green light around. And there you go. We have an indicator now. So this is what we're going to control. So, oops. I'm going to hook one wire to one side of this light. This is just a regular light that has, actually it doesn't even have a plus and a minus. It just has two terminals, and there is no polarity on this particular model. So I'm going to take one of those wires and it's going to go to the minus of our power supply. And I'm going to take the other wire and I'm going to put it to output 0. Now I'm not really going to go through the wiring on this because we have a lesson that talks about discrete wiring on the compact logic. So let me see if I can find that real quick, just in case somebody has a question about it. Let's see, reset. Okay, so here, if you have any questions, this one is discrete wiring to a compact logics. And there you go, just in case you have any questions about what I just did. Okay, the first thing we need to do is let's make sure, since I did this on the fly, let's make sure this green light works. So I'm going to open up my controller tags, and we are going to go to local:1 because this is, let's make sure we understand that. It won't take but a second, but yeah, so this is the base of our PLC. So this is 1, and then we had 2, 3, and we found 4 already, and we have 5. So I want local:1, outputs, and then data of 0. So we go here, and we find local:1, O dot data, and then I want 0 here. And I'm going to put a 1 in that, and a little small over there in the corner, but okay, yeah, we have a light on. And if I put a 0 back, whoops. Good thing Michael hadn't left yet because I just about shut the live stream down. I put a 0 right there and you see it goes off. 1 back on, and let me just make sure, just because you may not be familiar with that, all I'm doing here is in our data box in the controller organizer, right now I have a 1, lights on, 0, lights off, and I can go back and forth there. I'll leave that off now. So now, first, let's change our scaling a little bit, because typically we would not program with 4 to 20 milliamps. In other words, we're going to have some type of real scaling in the end. And so if we go back to here, what we're going to do is we want to change our scaling. So right now, our milliamp equation's right here. This is what we're doing. So if we want to change our units, we need to substitute the 4 with our low value and the 20 with our high value. And we are going to do a tank level here. So again, a tank level, and this in this case we're doing a pressure sensor. So tank level, pressure sensor. And this one, for this one, will be 0 to 10 psi. And on all pressure sensors, 1 psi equals 2.31 feet. And so that's what this is going off of. We're getting 0 to 10 psi. We're going 0 to 23.1 feet. So now everywhere that we have a 4, which is there and there, we need to substitute with a 0. So that's there and there. And then wherever we have the 20, which is only right there, we need to substitute with this 23.1. And that's how you can change your scaling on, really, you can change it to anything that way. So that's why I like starting with a live 0 when we're doing this. Because, okay, let's say we had, what's a good example? Like an ORP sensor. Those are usually like minus 1,000 to plus 2,000, something crazy. So they do have these offsets that you've got to deal with. They don't go from perfect 0. So now you know how to do it without going from 0. But yeah, in this case, we're going to go over here. And, well, I'm just going to delete out this DINT. That was just to show you why you need to use a reel. And then right here, oops. Oh, and okay, you notice it, yeah, right here, where is it? Right there. We're going to move this to 23.1 because that's going to be our high. And then we have the 4 right here. That's going to get a 0. And this one is going to go to 0. So that's going to give us 0 to 23.1. Let's go ahead and put that in and make sure we see that. Make sure it's working. Okay, Norm, yes. Norm's right. Only for a specific gravity of 1. I only work with water. But Norm's right. If you do that and you have molasses or something, or you have something insanely light, probably even alcohol or something, that's very or oil or anything, then that does change. So yes, for water, it is going to be a specific gravity of 1. But okay, so let's make sure this works. And so I'm going to let's go back and look at the analog simulator. And one, just, y'all don't even understand how crazy my screens look right now. I am going to make a change to the analog simulator just so that I can kind of look at the screen. As I'm going to go up here to settings. And first I'm going to change my range because right now I have it on 0 to 20, but we're actually only using 4 to 20. So I'm going to change that to, gosh, my wires are short, 4 to 20. And then I'm going to go here and I'm going to change my EU scaling. And I'm going to make my high engineering scaling. I'm just going to make it 231. That'll get us to 23.1, just so I can look at the meter and not have to like look in a crazy spot for this while I'm trying to show you this. So I guess it's the 23.1, and then our low 4 milliamps is going to be 0. And mainly now, if I go back to current 2-wire, then you can see that at 20 milliamps, we're showing 231 or 23.1. And we can drop down to 4. All right, and it shows 0. So 4 milliamps, we're showing 0 here. And if we go to our screen, then yeah, we're bouncing between 0 and some number that has that E and minus thing on it, which means it's a super small number, and that's all we're going to worry about in this video. And now I'm going to bring this up to 20 milliamps. And when we get there, then we are going to show, yeah, 23.1. We're right, this thing's right on the money. So that's how we're going to simulate our tank level. Let's see, hold on, Sean, what spec to watch for on power supplies that have reliable readings from 4 to 20 milliamps? Well, I'm not sure I follow you. Really, it's a 4 to 20 milliamps. So the maximum consumption is going to be 20 milliamps on that. Now, different voltages are going to be different ranges. And yeah, let's kick that can to the end here, and we could play with Ohm's law a little bit and show mainly you're going to have a load resistor. Every analog signal actually reads a voltage, and I do have a video on that if anybody's interested. Let me put a link to that video because there are actually no true milliamp sensors out there. Everything reads voltage. So let me see if I can find that one really fast. It's been a while since I looked at it. Oh yeah, here we go. Oh, that's how to wire it. Thought somewhere I had that. Well, I may not be able to find that fast enough. Well, actually, I guess I do talk about that. I think I've already posted this one. Really, it is the one about the load resistor. That's probably the best one. Is your none of them actually read a milliamp signal. So this same one of reading 4 to 20 milliamp with input. That one right there kind of explains most of that. Because yeah, okay, you can actually if you have let me watch this statement, because unlike a potentiometer, so if we had a potentiometer, which yeah we do have, and maybe we'll wire that if it really comes to a question. If our power, or 24, in this case if we had 24 volts, if it dipped to 23.9, it is going to throw that whole scale off. But this is one of the advantages of 4 to 20 milliamp, is as long as it is capable of driving that current, your voltage can go from probably 12 volt all the way to 28-ish volts, and it will actually regulate the signal the exact same. So that would be a neat video. That's not going to be for this one, but if I was to take, yeah, it's at the training center, so like most everything is that we need right now. But if I was to take a variable voltage power supply and connect it to the milliamp signal in the analog simulator in 2-wire mode, then as I vary the signal, I can probably go from 24, I can probably dip probably to 18, 17, 16. I don't know. I don't want to throw any crazy numbers out there, but I can dip that voltage and it will not vary the signal that we're getting. Yeah, Matthew, so you are right. And in that video, I explained that. On a 250 ohm load resistor, you are getting a 1 to 5 volt. Now, also, you'll see some of them use 125 ohms. That's going to be a 2 to 10 volt. So, yeah, Matthew is right. All any analog current input does is it reads a voltage across a very high precision load resistor. And I kind of explained that through there. Let's see, what could be the reason when a high level sensor tag value is reading negative instead of showing 0 and the tank is empty? Well, it's probably scaling. And I mean, even now, if we just go to here and I just take the wire off of this, look, we're going to show minus 5.73 volts here. So you're going to be negative there. But now we put the wire back on, because yeah, we have the open wire lead. That's pretty obvious. But even in this case, okay, well actually I'm going to have to make a little change for this one. As you remember, I just changed this to the scale of 4 to 20. Well, before that, we were on a 0 to 22 milliamp scale. So if I go back to ranges, current range, and I'm going to switch it back to 0 to 22 milliamps, that's going to give us our full range. And now I'm going to go here back to current 2-wire. And all right, we're at 20 milliamps. Let me bring it down to 4 milliamps. And okay, at 4 milliamps, we are showing right at 0. I mean, we're showing 1.76 to the negative 3. But okay, let me just drop it 3.9. Okay, now we're showing minus 14. And yeah, let me bring it down. Actually, a very common one is 3.2. That's going to be a minus 1.5. And that actually does usually mean something is wrong with your transmitter. Two ones that I don't talk about a lot is 3.2 milliamps and 21 milliamps. Those are two, you know, when you have a 4 to 20 milliamp, that's your normal operating range. But you can have 21, and on most of them, that means something's wrong with something connected to the transmitter. And then usually 3.2 is something's wrong with the transmitter. So, and yeah, those you kind of have to look at the manual. But okay, we want to do something now with this thing. We've got a green light wired up here, and yeah, okay, as cool as it is to watch these values run up and down, we need to run a pump. Yeah, that's what we're going to do. We're going to run a pump because we made this a level, and we'll make it a sump pump. And I see this a lot. Is the first thing somebody wants to do is, okay, they know they need to compare, so they go to the grader tab. And then we're going to bring down a grader. Let me bring down a new rung. And we're going to compare something. if this sump is greater than, oh, let's just go for 12. Just throwing a number at it. If it's greater than 12, then we want to run our pump. So we're going to look at our scaled ladder, and our source B is going to be 12. And then go to our favorites tab. We're going to bring down an output energize, and we're going to energize local :1:o.data.0, and let's put a description on that of pump. Actually, let's make this realistic. Let's change that description. Let's make this our expensive pump, just so we can have a little emphasis to this. And so now we're going to put that in there. All right, and all right, mainly this is going to work exactly the same. We've talked a lot through, go look for 1, go look for 0. This is going to look, is the scaled ladder greater than 12? If it is, it's going to pass true. Right now it is less than, so it's going to pass false. Now false output energize is going to go right a 0. And so now I'm going to bring our analog simulator up, and we see our value coming up. So this is just like water filling in a sump. And we get it close. So yeah, we're coming up 6. Oh, and I forgot. Hey, let me just show you what I'm doing. I forgot that I just switched that scaling back. I was like, my numbers aren't lining up. But okay, so you can scale this 0 to 21 milliamps, and that's what I switched to just to show that. I'm going to switch my range back to 4 to 20. That way now, mainly I'm looking at this bottom value here, and so we're at 12 milliamp. Oh, got to go back. So yeah, I'm going to change that back to 23.1 just so I can kind of look the right direction and still see this value. Which this comes in handy. Let's say that let's say our sump pit wasn't right at our PLC. This kind of lets us know what value we're simulating. And mainly now, if I go back here, okay. So we're showing 10.39 feet on this. And if we look here, then we're showing 10.39 feet. So, okay. Now we're going to bring up, so we need to be close to 12. All right, so we're coming up. We're at 11.6 feet. And let's just see how lucky we get, because this is kind of difficult to simulate sometimes. We're at 11.98. Oh, bring it up one more. Up. Man, guys, you are not looking out for my mistakes. This is local input 0. So I am turning on an input here. So let me change that. It's like, why is my light not coming on? This should be local :1:o.data.0. So 1, let me take this description out. Yeah, because this one is an expensive pump. Okay, now we're looking good. We have a green light on. And I'm not going to get lucky enough to show you. But okay, let me adjust this value just slightly. We're going to, actually here, I'm going to take this value. We're going to copy it. And then we're going to take this value and we're going to paste it right here. Because, honestly, this is what I did on my first analog job. It was for a heater. And my heater lasted like a half a second before it was toast. But okay, you see what's happening? Our light is just blinking on and off. And it's not doing that, but yeah, that's what I see, and that's what I did my first time. I put that in there, and yeah, I mean that heater was like bam, done. So what we've got to have is we've got to have a range. And so in a pump situation, typically you're going to have an on setting and you're going to have an off setting, or a high setting and a low setting. And so that's what we're going to do first here, is we're going to change this. And actually, let's go through some of the things I see done here. Because, okay, I want this to start. Let me put this back into let me get a drink of water here. And yeah, I haven't said it lately, but yeah, one, don't forget we are giving away an analog simulator to participants in this chat, or to, excuse me, to a participant in this chat. So all you have to do is participate. You can't say hi, you can't say anything like that. I mean, please feel free to say hi, but that doesn't qualify you for it. But we're going to select somebody at the end of this for an analog simulator. And don't forget to subscribe to our channel. We put out at least one automation video a week. And also, we're trying to do these live streams once a month right now to see, you know, that way you can kind of get some immediate feedback. You can ask your questions. And normally we'd be at the training center and I can set up something really fast for you. But right now we're making lemonade out of lemons, right, Michael? Okay. So now, I know I wanted this thing to pump when it's at 12, and then I want this thing to stop when it's at, we're going to say 5 feet. And what I see people do, and again, make sure you're watching all of this because this is not how to do this, is I'll see people go here and they're like, okay, I want it to stop at 5, so let me go and grab a less than instruction, and I'll see less than 5. And they'll put that in there. And yeah, this is going to do the exact same thing it's doing right now. So is 12 less than 5? Well, pretty much never right now. But this one right here is still going to cause this thing to flash on and off when you know we're at a point. Oh, now I did change that to 12. So it's not going to flash on and off. No, Vincent, it is evaluating this. So an analog signal is never going to stay exactly where it is. And that's what I did. Let me put that back just so you see that. Let me copy this value. And you can even see it. It's occasionally changing. And what I did was I pasted it right there. So I put it right on that threshold. And if we watch this, then it occasionally is dropping down. Now that we're done, yeah. In fact, here, you're not even, should we go on this rabbit trail? Okay, let's talk about that, Vincent. Okay, so we see this erratically changing, but you're right. Right here, we do not see this value changing. Well, what you can do is let's right-click it. Oh, sorry, you can't right-click it. You got to right-click the scaled ladder, and then what we can do is we can trim the scaled ladder. And this is going to give us a faster sampling rate. Now, this is not real time. I would not call this real time. But now we see that we're getting some variation. Let's right-click it and go to Chart Properties. And if we look at our y-axis, then we can change it. Let's put some custom, I'm sorry, not custom units. We're looking for decimal places. I'm just going to put 2, I don't know, let's put 3 decimals. I think that's enough to show it. And okay, now we can see this is bouncing between 12. Oh, I should have changed my scaling out. Go back here. Let's go to the y-axis. And let me bring this out to, I don't know, 30 seconds ought to be a plenty. Okay, now we can see. See, this thing is not, no analog signal sits perfectly. So this is occasionally dropping below our threshold and occasionally going above our threshold. So it's not really having to do with scan time as much as that analog signal. I mean, even the most perfect analog signal is going to drift some. And so that's what's happening there. And so, all right, but let's put this back. Because here's what I see people do is they want to fix this. Actually, well, you see it right now. Let me cancel out of this. As they try to get this to work. Because they're like, okay, I just need this pump to stop. So, you know, now we're going to be at the 12 there. Let me bump it up a little. So now we're solid running. Our pump starts emptying and it drops back down. Now, what people do is like, oh, well, I must put that in the wrong place. And they throw it up here. And, you know, and they put that in there. And I mean, I see that every training session we do, we see almost the exact same thing every time. Then they do this and they're like, okay, well now it won't run. Well, let's look at this. This says if it's greater than this 12.4 and it's less than 5. Well, can the exact same number ever be greater than this and less than this? Actually, I can do that, but that's for another video. But in this case, this can never be true. So this is always going to be off. And here's where you've got to begin to think about perspective. That's the word I always use is, you know, what did I say? I said I want this to be on at 12 and stop at 5. And that's what, you know, the engineer is going to tell you. That's what, you know, the customer is going to tell you. But we don't have a command. Oh, okay, well, and actually, John, nah, I wouldn't do that. So I wouldn't use a latch and unlatch in this case. But, okay, no, Scott, I would not use a latch unlatch. But all right, thank you for putting that in. But okay, the main thing, Michael, you still on over there? You're starting to zone out. Michael is just staring at his phone now, but that's okay. We're running pretty good, I think. Michael, what are you doing?
I'm paying attention to chat.
I'm glad you told me that that Scott and Vincent had both put those questions in. Thanks so much. But okay.
I'm sorry.
But okay. What I said and what the customer says is gonna Jeff, no. We would not use a limit there. And I will show you why. We will save that limit. Yeah, because no, that won't work either. We want it to start at 12 and we want it to stop at 5. Now, we do not have, and now we could use latch and latch, so it is kind of a stop, but we don't have a stop instruction. We only have a run instruction, so I'll put energize. So that's what you got to think about is when do you want the expensive pump to run, or in our case, the green light. So we know we want it to run if it's greater than 12. But what people do is they're like, okay, well, I know that other one's got to be less than. And they throw that less than down there. From the perspective of running the pump, we never want the pump to run when it's less than 5. So there should be no instruction in there that has less than 5 making that output true. So that way we know it needs to be greater than. And if we flip back over here, that means that, okay, if we always want it to run when it's greater than, we know this one needs to be greater. And then, yeah, it kind of, you know, most people get it to right here, and then they're like, I don't know what to do. Jeff, we're going to come back to your limit, because your limit's going to do the exact same. No, we are not going to use a delay timer. That is absolutely the wrong way to do it, and I do see it done that way. And there's lots of issues with the delay timer, because mainly I want it to run between 12 and 5, period. But okay, they get it to here. But here's the thing you got to think about it is when do we want this pump to run? We want it to run when it's greater than 5. And then, okay, we said stop, greater than 12. And we said stop less than 5. So we want it to run when it's greater than 5. And if the pump's running, continue to run until, as long as it's greater than 5. Let me put that in there just so we can see that. So we got this part. We change this back to 12, so 12.0. So we're going to run if it's greater than 12. That's going to get us starting to run. And we want it to continue to run as long as it's greater than 5 and the pump is running. All right, well, let's see if Michael's delay thing works. So I need to wait 10 seconds. How can we know that our pump is running? Can anybody tell me? Do we have any instruction to know that our pump's running? You can count to 10 for me. Keep him awake. He's starting to die. He's getting hungry. Had that 30-minute delay. Oh my goodness. He's leaving.
I'm leaving.
Okay, how can we know this pump's running? Well, we've got instruction to do that. We go over here to our favorites tab and we have this examine if on. There we go. Scott got it. Yes, add an XIC. That's it right there. There we go. There you go. All right. Norm's got it also. So we're going to go here and we're going to put this here. And so this is going to make us run in a range. So now, first notice our pump's not running. So we started a good place. Right now we are, let's see. Yeah, absolutely, Vincent. You're absolutely right. But okay, so right now our pump, we're at 11.8. You can see there, or 12.2 milliamps, and don't know if you can see it perfectly there, but that is 11.8 feet. And if we go over here, we can see that just as well. As right now, our ladder scaled is at 11.8 feet, and it needs to be greater than 12. So right here, this instruction is going to look if it's greater than 12. Is this greater than 12? No, this is false. So this gets to right here, and one thing we haven't talked about in a while is once it gets to this leg right here, it does not move on depending on the condition. So if this was true, it would not move on. It's still going to come back to right here. And now it's going to evaluate this. Is this scaled ladder greater than 5? Yes, it is. So this is true. And it gets here, and okay, is our expensive pump a 1? And we can mouse over just to make sure it has a value of 0, so no. So this is false. Now for this to be true, we have to have a continuous path of truths from left to right, and we don't. So a false output energized is going to go right as 0 to the green or expensive pump. So now I'm going to bump it up, and if we do, actually, yeah, this is where we were, but okay, we're at 11.98. Bump it up one more, and okay, now we're at 12.1, and our expensive pump is running, and we got this lower branch here, and this is looking for this to be greater than 5. We know that was true before, it's still true, but now this has a value of 1 in it, so it is true. And so we have a continuous path of truths in the top statement, and we have a continuous path of truths in the bottom. And now, but let's drop this down. So I'm going to drop it down a few just so we don't get any bouncing. And now we're back to that 11.8. So is the scaled ladder greater than 12? No. So this is false. But it comes to here. It's going to go to the next branch down. Is the scaled ladder greater than 5? Yes. So this is going to be true. And then this instruction goes look for a 1. Does it have 1? Yes, it does. So this is true. So now this bottom branch is true. And it's going to keep our expensive pump running. And so now it's going to start emptying our sump. And yeah, we're going to see it go down. And we're going to get to... let me get it close to 5. Oh, we're at, come on. There we go. We're at 5.91. Now, let's just talk through this again and make sure that we still understand this. So this instruction is going to look if the scaled ladder value is greater than 12. It is not. So this is false. We get here, and it goes down to this branch. And this is going to look for our scaled value to be greater than 5. And it is, so that is true. This looks for a 1, and yes, it still has a 1. So this is true. So this bottom branch is still true, and it's going to write a 1. Now, when I drop this down just a little bit more, it's going to make this go to 4.9. And so next one down, 4.9. Now, this goes still, it's looking for it to be greater than 12. It doesn't, so this is false. Gets right here, goes down. This looks for it to be greater than 4.9. It is not, so this is false. And it gets here, and it's going to look for it to be a 1. Well, it is not now. And so since this is false, it's going to go right as 0. So in this case, all three of these conditions are false. All right, now here's the trick part to make sure we understand is now I'm going to bring the milliamp signal up back to 5, above 5. So again, this is going to look for it to be greater than 12. It is not, so this is false. Gets here, it's going to go down, and this is going to look for it to be greater than 5. Well, this is, so this is true. But now it's going to go to this, and this goes and looks for a 1. Well, it doesn't. It is false. So this is going to be false. And that means that this is going to be false, and it's going to go right as 0. So at this point, there is no way for this lower branch to ever be completely true until this is greater than 12, because we've got to have this top one to go. And while we're at it, just so we can see this a few times and I don't have to sit here and scroll up and down, is while we're simulating a value, I can hit the OK button, and that's going to bring up a few options here. And I'm going to go to this sweep cycle right here, and we're going to go, let me just make this really fast. We have a sweep time, and it's typically 20 seconds. I'm going to bring that down to 5 just so we can quickly run through this. And then we're going to have a start value, and okay, I probably should have noted our value, but I didn't. So we're going to just go from 0 to 20 milliamps. Actually, no. Well, we know we're going to go from 4. So our start value is going to be 4. Okay, and actually let me look that up because, yeah, let's get this a little more accurate. So we know that, let's see, we want to go to 4.9 just so that the pump kicks off right when we drop down. That's 7.4 milliamps. So I'm going to go back in here and we're going to go, and our start value is going to be 7.4. That's our low value. And then we're going to have a high value. And so let's go back out. And let's bring it up. And I just want to see what's 12 milliamps. I'm sorry, what is 12 feet? So 12.5 milliamps is roughly 12.2 feet. So I'm going to make our final value 12.2 milliamps. And what this is going to do is it's going to simulate a sump now. And so if it gets above, it's going to just run between 12.2 and that, just so we can watch this a few times and make sure. So we're going to run this cycle. And right away you can see that, yeah, our green light, well, hopefully, I may need to bump that up. Yep, I didn't get my scaling right. Oops, yeah, so my final value is too low. I think it was 12.5. Now let's run it. There we go. Green light comes on. We should see the green light go off. Okay, now let's look in the program while we're doing that. So we see it going down. All right, now it's climbing up. That's a little fast. So let me go in here. And let's just change that scale, that speed a little bit. That's a little too fast to explain this. I didn't want to bore you with it going up and down. Let's change that to about 12 seconds. So that'll make it where it runs from top to bottom in 12 seconds. And so now we filled up, our pump kicked on, it's going to roll down, it dropped below 5. Now it's filling back up, kicks on, and it keeps going back and forth. Hey Scott, you know, the vertical, actually that would be, like vertical, you mean horizontal? Vertical tank capsule. If it's round and it goes up, then we're going to use the same scale we have. The horizontal one's the one that gets a little iffy. But no, this scaling right here will work as long as it's same shape up and down. But, you know, it would be interesting to do one on different shapes. And since Norm brought it up, I think it was Norm, different specific gravities, things like that. That would be a neat one. I don't think we'll get to that one in this one. Okay, has anybody got any questions on this part? Now, what Jeff Kuiper brought up. Yeah, okay, gotcha. Yeah, and that's what, yeah. So, yeah, when it's not, yeah, that can get tricky. All right, Jeff Kuiper did bring up one thing. And, you know, Scott, that would be a real, I'm going to make a video on that. I don't think I can pull that off with the visuals I have right now. I need to make some drawings and explain a couple of things, but that's one that'll stump you. Now, Jeff Kuiper brought up that we, what about a limit instruction? Well, let's do a limit instruction just so we can see how to do it too. So let's just take our expensive pump out. Actually, yeah, we're just going to test this one. You're right, Vincent. This is exactly the same as a seal-in, and that's, I think that's the thing to kick into people's heads here, is this really is not that different than an XIC as far as its evaluation. It's going to be true or false. And then the exact same thing. We have that seal in here. So whether this is an XIC of, you know, a float or we're looking at a level value. Yeah, it's exactly the same. All right, so I'm going to take this out and we're going to change this instruction, which if you didn't know, you can double click right here. One, you can right click and we can, oops, nope. Can't right click there. You couldn't 500. You can't here. You can double click right here and I can just type LIM. That's going to give us a limit instruction. And we're going to put our test, oops, we're going to put our test at the scaled ladder. And our low is going to be 5. And our high is going to be 12. And I see, and this is something else that you see people do when they're doing it. But okay, we're going to put that one in, and we'll see how it operates differently. Oops, I didn't want to finalize that because I want to go back to where we were. Let's change, oh, where was I? Let's just use the test button because I'm going to back this right back out. So we're going to test that edit. And okay, the big difference you're going to see now is, okay, did you see that flicker? Let me, that's right, you've got it, but let's make sure everybody else sees it. Yeah, did you see the bounce there? So now what's going to happen is that time that it drops below 4.9 mainly, it's going to kick off. Also with the limit instruction, if the sump goes above 12, it's going to stop running. So, but that is something you see people program in. So, and that'll happen. So next thing you know, they're at 12.1 and their output doesn't come on anymore. And yeah, their simulated sump just keeps filling up. Now I made this one really limited for that. So this works really well when someone wants to input a start and a stop. Now what I see happen though, and you know, some people you just have to deal with this on, is especially on temperature. Somebody will say, I want exactly 350 degrees. Well, there's no such thing as exactly 350 degrees. It's going to be plus or minus something. So yeah, Sean. That I think I don't know why I haven't actually ever done that, because I have some programs that deal with the round and the flat bottom, and also the oh, my mind just went blank on the tapered, you know, the cone style bottoms. But yeah, that does change your level sensor, and I've got some programs that deal with it. That would make a good video. Michael, write that down. Okay, but all right, let's get this out of here. So let's just cancel this edit and put it back like it was. But okay, let's say somebody says that, and it'll be, oh, let's just make it a chiller actually. Somebody has a chiller and they want to regulate something to exactly 350. So just for the exercise, let's make sure we understand how to change the scale in here. So if we go back to the, whoops, where'd it go? I'm really struggling with my screens here. They're the wrong direction. Okay, so remember, all we got to do is change where these two values were to whatever we want. So had you not used the PID, you wouldn't need a PID for this, Vincent. Not for the not to do the scaling. We can do it with some calculate, and that'll be a fun exercise. I'm going to do that one because yeah, we can get into some fun math, and I like doing some fun math occasionally. Not that often, but occasionally. But okay, so mainly here, let's change this a little bit because I just said we're going to make a chiller. So let's make our scaling 0 to 1,000. So mainly this 23.1, we're going to change to 1,000 just to give us something else. So we'll go over to our program. We're going to go up here, and where we have 23.1 right here, we're going to go to 1,000. Also, this light flashing back and forth on me is kind of bugging me. So let me show you. Actually, let me show you a couple things on that. I was getting ready to turn it off. But while we're at it, let's say that we're watching for something, and all of a sudden we see it. And that moment we see it, we can hit the OK button. We can freeze this or pause it right where it's at. So it's at 11 milliamps now, and it's not moving. And then I can hit the OK button again, and I can resume simulating. So sometimes when you're trying to capture something really fast, that's a very useful feature. But okay, for now, I'm just going to hit the cancel button. We're going to get out of all this just so that we don't have to see that thing going up and down. But all right, let's go back here. Whoops. Where are we at? There we go. Okay, so that's going to give us 0 to 1,000. And okay, we're doing a chiller right now. So in the case of a chiller, we're going to want to cool when our process variable is greater than something. So same deal here. It's going to be exactly the same as in this case. all right, the customer said he wants 350. And that's what he wants. Now first, and here's where, you know, here's my poor little heater application. First time I ever messed with analog. That's what the customer said. It may have about been 350, but he said we had to hold a precise value. And so I threw that in there. And as you've already learned, well, let me get back in here and simulate a value. As we're going to bring it up close to 350. And let's see if we can get lucky and balance. Look at there. And there you go. Here is exactly my poor heater application is my light. Whoop, there it goes. Except for mine was flickering on and off like, you know, I have known many times. But I've never seen a heater burn up so fast in my life. So what we've got to do is we've got to have something in there to stop this chattering really. And then what we're going to do is we're going to use a span. But let's say the customer, he wants this, either he thinks he needs this at 350 precisely, or he only wants the operator to enter one number. We'll have another hidden number in there. So let's talk about how we can do that. Okay, Dan, we went through the lim instruction. That's not going to work. Just later on you can back up a little bit here, and yeah, we went through that lim instruction, and yeah, that's going to cause you all types of grief. So here we're going to use this, what we call a span, but we don't want the operator to enter the second value. So first we need a value here, and so let's make this our temperature set point. Oops, where'd I go? There it went. That point. And we're going to need to create that. And we want this to be a real, that we can enter a decimal if we wanted to. But now what we want to do is we're going to add something else, because what we need to do is when we this heat, or sorry, in this case we're chilling. I gotta make sure I always get this backwards and okay. We want it to, we're going to use this subtract. We want it to cool a little further before we shut our chiller off. Now first, let's go and change this. It's no longer expensive pump. This is our expensive chiller. And now what we're going to do is we're going to go to our math tab, and we're going to bring down a subtract instruction. And we're going to take this temperature set point that the operator is entering, and we're going to subtract it by our temperature span. And we'll create that as a real number. All right, I think I got it under control. You want to go eat lunch? All right, get out of here. All right. Thank you, Michael, for all your help. I think as soon as he leaves, things will go bad. So keep your phone with you, please. But he's going to go get lunch. All right, and then we're going to need, in this case, let's call it, well, this will be our, let's call it our temperature, I don't know, off. Temperature off. That's just what I would call it because I can't think of anything to call it right now. And we're going to create that. Now, same deal. We're going to do that exact same seal-in that we just were using. And now, same thing. Make sure you don't throw, there should not, almost never should there be opposing here. If you have a greater than in the top rung, your bottom one's going to need to be greater than. But now we have this temperature off setting, which is our temperature turn off setting. I probably didn't use a great description for that, but that's going to be this bottom one. And then, yeah, we're going to put our XIC back in just like we just had it. And we're going to bring that down. And okay, so one, let's put this in just like it is. Just so you see it's going to do the exact same thing right now. Because, ooh, I made a mistake here. Anybody catch it? Actually, in a crazy sense, this actually would work, but there's a problem here. This is only going to do this subtract when one of these statements are true. That's not good. That can cause us some issues. So either this needs to be around the whole thing or on its own rung. So I'm going to bring another rung down. And I'm just going to drag this subtract. Come on, computer. My computer's choking up on me. Bring the subtract down to here. That's what I should have done. Take that branch out. That way our span is always calculated. Put that in there. Okay, and now let's put our temperature set point in because we need a set point, and our customer said 350 degrees. So there we are, and first, if you can't see it, you won't notice it. Maybe you can see it in the corner here. Our green light's on, but occasionally this light's blinking and you're not seeing it up here. Remember that this is not perfectly real-time representation. So if we go here, we can see this is blinking. And that's because we have our span at 0 right now. Now, so what we got to do is we got to figure out a span that, one, is going to be acceptable to the customer, but also is going to save our equipment. Because right now we're hammering this thing on and off. And the less on and off transitions we can make, the longer our equipment's going to last. So we want to go here, and for now, I'm just going to throw 20 in here. Again, just so we can kind of see what's happening. All right, so now let's look at this. So this is 350, and we already saw this is occasionally dropping to 349. So this greater than is going 101010, which is changing this beforehand. But now we have our lower branch again. And now if it's greater than 330, this bottom greater than is going to be true. And if our expensive chiller is running, it's going to continue to run. So what this is going to do is when our temperature gets above 350, it's going to kick our chiller on. And now we have this span here, and that's going to keep us running until we drop down to 320. So we drop down. We'll bump back up on 350. Let's see if we can get kind of right. So there's 337, 343, and there we go. 350. Pump comes on. We drop to 343 again. Pump stays on. Our expensive chiller stays on. And yeah, 331, and there, 324. It kicks back off. So that's going to keep us. It's going to save our equipment. And really, you want to almost, I hate to say it, you want as much span as possible, and you can stay within tolerance. That's going to make your equipment last longer. Now, we could also use some solid state things here and some PIDs, and we have a whole lesson series on that. But right now, we're just talking about some basic pumping. And now while we're here, let's talk about what if we wanted to run a heater? Because it's going to be exactly the same. But in the case of a heater, instead of us trying to cool or us looking for a temperature to be greater, now we're just going to look for it to be less than. So let's edit this run just so we can see it. Let's change that to a less than. And then same deal. Whatever's in that top branch, if you're doing some type of latch or a seal in here, it's going to be the same thing you want this bottom one. And then let's change this description. This will be now our expensive heater. Now the one thing you have to pay attention to is now the span in the next rung. Is typically you want, now this would actually work. This will work just fine. But what you want to do is you want the set point that the operator enters to be when he sees that on action. It's going to keep him from asking questions. So in this case, I want to add now. So what we're going to do is we're going to kick the heater on when we're below a temperature. And now we're going to keep heating until we get above a certain temperature. Let's throw that in so you can see the values change on this. All right, now our high is 370. Now again, this may be way too much range. Y'all may be like, well, who wants an oven that's between 350 and 370? I'm just making these values wide so you can see exactly what's going on. But all right, now our span is going to be, we're going to start if it's greater than 350. And they're going to keep running until it's at 370. So we're at 324 right now. Our heater is running. So our heater is running. It's going to start raising our temperature. And we're going to get, there's 350. There's 356. We're still running. Now note at this point though, 356 is greater than this temperature set point. This is false. This one is true. And we're going to bump this on up. And there you go. When we hit 375, heater goes off. Now it's going to coast back down, 349, and it's going to go back up and back down. Lastly, John, PID is good if there is a delay between the input and output, especially when things can overshoot like temperature. Yeah, and and actually that's not on my list, but so you can have, we'll call it a pulsed output, and you can actually have a solid state relay that's kicking on a heater. That's not that uncommon. As opposed to a 4 to 20 signal. So I should add that to the PID series. but okay. Hold on a second, somebody's coming. They must be going the other way around. Okay, but all right, so that covers the heater, that covers chilling. Okay, let's talk about a couple other things though. So yeah, one, early on, and yeah, it's been too long now, I can't even remember who it was, but somebody asked, well, where is the scale instruction? There is no scale instruction in this Studio 5000's ladder logic. Typically you're gonna see, you could see some math things done. There are many ways you could do it. But what you can kind of see, and the way I really, usually if I'm doing something like that, there's several reasons to need function blocks. Now, nowhere in that statement did I say I would write a 100% function block program. But what I'll do is we're going to right click, add a new routine. And we're going to call this routine our function block. And we're going to make that type a function block. So now we've created a new routine. Open it up, and this isn't an exercise in program flow, so I'm not going to go too far on this, but mainly we see we have no green here, we have no green here. That means that there's no possibility of this being scanned. And actually, even can I verify this while we're online? I think it's going to give me the warning again. I didn't point out that warning, function block routine cannot be reached by main routine. And what that means is we need a JSR up here in our main routine. So I'm just going to go here. I'm going to add another rung, and we are going to put a JSR, and we're going to go to that function block routine. That's going to get that one scanning. Also, just so we can go through hit the basics, I'm actually going to change our 4 and 20. We're going to go back to 4 and 20 here. So we're going to have 4, and this will be 4. And then this one is going to be 20. That'll put it back at our 4 to 20 milliamp scaling. And then, yeah, before we go further, let me test that. So I go up to 20 milliamp. And that is going to give us 20. Can you believe it's starting to thunder here? Are we really going to have another power outage? Okay, but we only got a few more things to go here, so hang with me. And the power goes out again, guys. I'm done for the day. Okay, and I go down to 4. And yep, we're showing 4 milliamps. So that's back like it was. So let's talk about how we do this in a function block. So we go here, and I go to Edit. Then if we go to our Process tab right here, and now we have a few different instructions than we typically would have. And mainly the second one is going to be our SCL instruction, our scale instruction. And you see we have an in and an out. So our in is what do we want to scale? And that was our raw value. Now, you see how when I get near these, they highlight green. So I'm going to drag that to there, and that connects those. And then we're going to do the same thing on the other side. We're going to have an output. And okay, now if we go here, we're going to have local colon 1, oops, local colon 4, colon I dot, oops, let me just use the drop down. Where am I? Wow, there it is, channel 0. So that's that. Now one thing by default, let me get through this part first. Yeah, so our output is going to be scaled function block. So it's going to be a whole new tag. We're going to create that, and it's going to be a reel. And one thing I don't like is by default, or did I? No, I didn't. Okay. One thing to watch out for is, let's say, let me go and add a description here, and we're just going to put, actually, I'm going to put a description on this one because this is the one that's kind of confusing. This is our analog input. Oops. And click off. By default, it doesn't show the descriptions. And I don't know exactly why they did that in Studio 5000. But if we go to options, typically yours is going to look like this. And you're not going to have these descriptions. And I'm not sure why, or I don't know what the advantages would be. But if you don't see your descriptions, go to options and look for that show tag descriptions right there. Also, another one that's important, and I don't want to get into in this video, they don't have show alias information shown typically. And I think that's another important one, but we'll talk about that one in another video. But okay, so this is going to take our analog input and it's going to scale our function block. And if we look here, we have block properties, and we're going to click there, and we see we have raw max, we have raw min, we have engineering units max, we have engineering units min. And so if we go back to our original thing here, then we know that, let me go over, where's the slope? Yeah, we have a ratio here of our 4 to 20 equals 32.7 to 16.383. Well, these are those numbers. So our raw max is 16.383. Our raw min's 32.77. Our engineering max is 20. Our engineering min is 4. So in this case, and this is where, you know, people who are diehard ladder or diehard function block or diehard structured text, you know, I can't agree with any of them because, you know, they all have some really key advantages. So our max raw is going to be 16.383. Our raw min is going to be 32.77. And then our engineering unit max is going to be 20. And our engineering unit min is going to be 4. And let's start by just throwing that in. And we know we're at 4 milliamp right now. We put that in, and okay, it's 3.998. Well, let's open up our controller tags just so we can see. We go down. Where's the scale? Oh, did I put the all right, so I made a mistake. I put my no, I didn't. I'm just blind. What did I do wrong? I just created that. It just needs sorted. Now they're both side by side. So notice these numbers, the scaled function block number and the scaled ladder are identical. I'm going to run it up to 20 milliamp. And there you go. We're right at 19.998. But mainly they're exactly the same. So this equation right here, all this craziness is done by this simple scale instruction. So I would absolutely use this scale instruction normally. I would never do this compute. Now there's a few exceptions to this though, and that's why it's important to know this, is if you have Studio 5000 Mini, then you are not going to have access to function blocks or structured text. You have to have at least light to get those features. And yeah, you can argue that they should, but mainly Mini is a super economical way to get into this. I think it's $366 a year. You can be in Studio 5000. Everybody keeps telling me, oh, it's $10,000 for Studio 5000. No, it's not. It's like $350, a little over that every year, and you're good to go. But it won't have that function block. So, and you may see this, some people prefer ladder, but I would absolutely do this function block. But while we're here, let's look at a couple other things. Is right now we're at 19.998. Is we have a few cool features. I'm gonna take this. Oops, let me take my range back to 0 to 22 milliamps because the analog simulator by default is not going to let you go out of range because sometimes you don't want to. You remember I changed that range earlier. So I just changed it back to 0 to 22 milliamps, and I'm going to go back in here, and we're right at that 20 milliamp mark. Is I'm going to bump it up to 20.1. All right, and first let's look here. If we go to our controller tags, then we're showing. Oh, I keep having to scroll back down, but okay, they're identical numbers. Actually, interestingly, there is a rounding issue in the 7th decimal place. That's kind of interesting. That's all I can say about that. But so, okay, there's a slight difference, but it's not enough difference for anybody to worry about. But let's go back here. Is we have this max alarm and min alarm. Notice our max alarm is now a 1. So we can use this and alarm if our sensor is above 20, because typically above 20 means something is wrong with your milliamp circuit. And if we go down to 20 milliamps, notice as soon as oops, let me get off of that. Oh, come on now. All right, so let me go back up. So notice, all right, we're above, we get a max alarm, and also if we go below, 4.096. I drop it one more. And now we're at 3 point. We get a minimum alarm. So that's going to that's going to let us know that something's wrong. And if we go back to our controller tags, you can see they're sticking right together. Now here's something cool you can do with a function block. And let's say that for some reason, and I'm sorry guys, I'm not remembering who said what. I wish I could screw man. I let Michael go to lunch. That was really bad. Somebody was asking, what does it mean if your value goes negative? Can't remember who it was now. And yeah, I can't find it fast enough. But if you have that problem, and you're like, I have no idea why, but I just wish it quit doing it, we have this limiting right here. Is we can change that to a 1. And I'm going to hit the apply button here. And notice now our value is 4. And if we go over here, because now we can see our real value and our scale value, our value is 3.896. But the function block is going to limit it to 4. And now I bump it up. Now we're going to line up together, but watch what happens when I get up to 20. All right, we're at 19.9. They both look beautiful. We hit 20. They're 19. All right, they're actually 19. Yeah, they're right at it. So these are going to hit close. But now I'm going to go to 20.1. Notice this one is fixed now at 20. And I can bring this on up. So we can get all the way to 22 milliamps. Or 21.1. So it's fine. Okay, and that's the limit. That's the range of this module is 21. But okay. We can do that, and we're sticking at 20 here. So that, okay, Trex Controls was one that I was asking. So that's how you could limit it, Trex Controls. If you're like, I just don't know why it's happening, you can use that to limit it right there. Now, I'm not going to limit it, so I'm going to change that back. Whoops, where'd it go? There it is. I'm going to change that back to a 0. I'll apply that, and that's going to throw it back up there just like the other one is. Now, we also have structured text, and this is one that kind of, I kind of laugh a little bit when people complain that structured text has 0 use. Next thing I ask them, well, what do you think of the compute statement? Oh, the compute statement is the greatest thing there is. Well, guess what, guys? The compute statement that we used here, and you know, somebody smart at Rockwell may even would tell you, is the way I see a compute statement is it's a mini subroutine with one line in it. And it comes right back here. So we're going to right click, new routine, and this is our structured text. And it's going to be a type of structured text. And then we're going to hit this JSR here, copy, paste. Get ourselves a structured text. And actually, while I'm here, now watch this. All I'm going to do is I'm going to copy this. Control A, Control C. Actually, make sure you saw that. Right click, copy. All right, we're going to put those in there. That's going to get our structured text routine running. And mainly, I didn't do anything to this one. It's the exact same as it was. I just copied it. Now I'm going to go down here to structured text. Oops. Okay, I was looking at this warning. That kind of threw me for a second, but we put this in after that. So here's our structured text routine. I'm going to hit that to edit it. And we're going to put scaled. Now notice the function block of the ladder and that ladder dent we made are here. I'm going to put structured text. And then you put colon equals. That's how we put an equals. If you just put equals, that's a compare statement. Colon equal means go write something somewhere. So colon equals means whatever I put after this, you're going to write to that structured text. And now I'm going to put paste, or actually I'm going to right click so you can see exactly what I'm doing. I'm going to right click right here. And I'm going to hit paste. Bam! That is exactly what is in our compute statement. And then here at the end of it, the only thing, and I forget this probably, I probably forget this 75 to 90% of the time, is you got to have a semicolon at the end of this. Now the only thing is, I just typed this, scaled structured text. So we need to right click it, and it's new tag right there, just like we normally do in all the rest of them. Again, I'm going to make this one a real. Okay, and now we're going to put that in there. And now we go to our scale values. Let me close that up. Close that one up so you don't have to scroll so much. And, oops, what did I do wrong? What? Oh, again, you got to sort. Once you add it, it adds it to the bottom. Okay, now we have a scaled function block. We have a scaled ladder. Okay, that scaled dent's in the way. We're not using it anymore. So I'm just going to highlight it. If you didn't know, if you're not using something, you can highlight, right-click, delete. Bam, it's gone. Make sure you know that there's no verify on that. That's probably something we should do in a video. Is yeah, with that delete button I just did, that thing is gone. No more. There's no undo on it either. Okay, but now look, all these values are identical. And so yeah, we'll drop it to 20 milliamps. And yeah, we're still 19.9998, which is pretty close. And we're going to drop down to 4 milliamps. And at 4 milliamps, there you go. They're all identical, right at 4.01. So here is how. Here is a compute statement. And yes, a compute statement is a mini structured text routine. So if you say you hate structured text and you think that the compute statement is awesome, then you have a crisis on your hands because they're the same thing. Here it is in function block. And I'll admit, function block is the best way in Studio 5000 to do this scaling, in my opinion. And you have structured text. And honestly, this, I can't knock this. Now, I do need to knock one thing, because here's another thing that's not there by default, is I'm going to right-click. Where is it? Am I right-clicking in the wrong place? Options. John, do I have a recommendation on where to learn structured text? We're actually getting ready to do a structured text lesson series. Some basics, they're going to be a lot like this, they're going to be Rosetta Stone type things. So we're going to show how to do something in ladder, we're going to show how to do something in function blocking, we're going to show how to do something in function and in structured text. So we can see how they function exactly the same. But there is an issue here with structured text and Ruckman. And this is, I don't know why they do this. Except for maybe it does, I'm not sure why. Inline value display by default is do not show. So by default, you're looking at this, and this is why people don't. This is what gives structured text a bad rap, I think, in Studio 5000. If I was looking at this and I want to know what my value is, I can't figure it out. I can mouse over it and get a quick snapshot. I can mouse over this and get a quick snapshot, but I can't see the actual value. In fact, let me make sure you see that. Right now we're 3277. I just bumped this up to 5. It still shows 3277. I'm going to move off of this and move back onto it. And now we can see the new value. And yeah, over here we can see the new value. But it does not live update when you mouse over this. So there's a couple things we could do though. Is one, I can right click structured text right here. And I can watch tags. And now I can type scaled structured text. And bam, I can see the value there. And then I can go ahead, while we're here, let's throw local :1, oops, not 1, 4, I dot channel 0 data. And there's your two values. The watch window can be very useful in this. But I personally like having this show, at least show and monitoring. Maybe in show always. And here's where I think show with monitoring is probably the great compromise. Is show with monitoring, or for offline, it keeps everything compact and your line numbers are really easy to see and it's easy to compare things. And yeah, I think this is just so valuable. But you could do a watch window, but now we can see every value. But all right, we've got a little, we're nearing the end of this. But okay, while we're here, let's talk about one other thing. What do we have right now? We have a heater going, and this is back to 4 to 20 though. So let's make this 12, and let's make this 8. Oops, nope, we're using a span now. Let's make this 2. And, gosh, all right, put that in. I didn't need to edit that wrong. Okay, there we go. But okay, now we're at 5 milliamp and we're looking for 12. Oops, actually we need to... Let's see, yep, let me go up now because we're heating. So we're bringing this up and bringing it up to 14 milliamps. There, kicks off. So this works exactly the same, only now we are in milliamps instead of the value, you know, the kind of real world values we had. There, it kicks on, kicks off, exactly the same. But now let's talk about how we would do this in function blocks. So right now, if our value is less than the temperature set point, and here's where you can start talking this out and figure this out. If it's less than the temperature set point, or, so this branch is an or, it's less than the temperature off, and the heater is on, then we're going to turn on the heater. So let's talk about how we could do that in function block. So let's bring down, let's find a less than. So if we go over to our select limit, oops, not select limit, no, compare, then we're looking for a less than. So same deal, we're going to edit this. Now let's get rid of the watch window. And we're going to bring down a less than. Well, I'm glad you like it, Vincent. Let's see. Okay, so our source. Now notice, you know, here's where, you know, you just got to learn the differences between them. Is all right, so we have source A and source B, but we've got to use those input things, or we've got to use some direction here. And so we're going to go there. We're going to bring this down. It's going to go there. And we're going to connect these. And so our first one, okay, first this is our scaled function block value. And then this one is our temperature, oops, not temperature off. What was it? Temperature set point. And yeah, I know it's not a temperature set point now, but and yeah, I can change that. There we go. We can edit it. This is now our milliamp set point. There you go. If you didn't know you could change tag names on the fly, now you have it changed to there. So if it's less than that, so this right here is going to take place of this right here. Okay, now we have this piece. So we have an OR statement. So we're going to go back to our function block. And we need an OR. So if we go to our favorites tab, right here we have BOR. So there's our OR. And this was that top one. And then we had another less than. Now if you notice though, we had, get my tabs organized here a little bit. Move that over there. There we go. Now I can bounce back and forth fast. Here's the OR, but I notice we had this AND in here too. So we need to put the AND statement in here, and that's right beside of it right here. There's the B AND. So we're going to bring that down. And this is that second condition. So there we go. And notice we have 3 extras here. You'll just hit this view block properties. You can uncheck the ones that you're not using. There you go, and that tidies that up. And okay, so now we need another less than. I'm just going to, actually no, I'm not going to copy and paste. We're going to go up here and find it. And compare. And we bring that down. Now you notice, now that I'm not a very neat function block maker. So somebody probably will get upset with me actually. But yeah, let's get at least halfway lined up. So put that there. You can bring that up, line it up there. And then, yeah, this less than probably should be right here. And then we need a couple more inputs. We're going to bring that down. Bring another one down. And yeah, I should line these up really neatly. Oops. Yeah, you're not going to get a lot out of me on neatness of lining these up. But we're going to put that there. Put that there. And okay, this one again is that scaled function block. Okay, and in this case, right now it is temperature off. We're going to change the name of that as soon as we get it up here. So now we're going to right click, properties, and we're going to change the name of it. That's going to be our milliamp off. There we go. And now we have an and here. And our second condition was that our, well, expensive heater, we'll leave it as an expensive heater. Our expensive heater has to be a 1 or has to be on. So in function block to do that, first of all, this is going to connect to here. That's our first condition. And yeah, we'll line that up. And yeah, probably should line that up something like that. And then our second condition is going to be that output. So I might be able to get it right here. I'm never really neat at this. But local colon 1 colon O dot data dot 0. That is, okay, and yeah, can't have the expensive heater up there because the text gets truncated, but we're going to put that there, bring that there, and again, ugh, that's really bad. I won't leave that. I'll drag that out and get that neat there. Then we'll hit the B, and we're going to take those 2 extra conditions out. And then we'll put that in. And all right, we got to do something here. I want this where you can see it. So this will be our expensive heater. So it is local colon 1 colon O dot data dot 0. That's our expensive heater. Now let's get our main routine and let's change this one. Just because I need this. I don't want to duplicate output. That's for another lesson series. So I'm going to change this to output 1 just so it's not going to be controlling our expensive heater. But okay, now we get our function block. Let's look at this and make sure we understand. So now, if our scaled function block input is less than our milliamp input, then we're going to end up with a 1 or a 0 here. And this is our true or false here. And in this case, if it's 1, if our selected function block is less than our milliamp off, then we're going to get a 1 or a 0 here. And this already showing a 1 or a 0. And that's why I kind of do like function blocks. Now, we do need to talk a little more about that. I didn't say you should go out and hog wild use function blocks. But there are some things about its logic that I really love. And actually, I usually bring over to ladder. So put that in there. And first, let's see if it works exactly the same. Our green is on. And we are at, so right now, our heater value is less than, or I'm sorry, our milliamp value is less than 12. So this is true. And it's represented really well by this 1 right here. So we know this is true. And then we have an OR statement here. Now it doesn't skip still. There is a process that goes through, and I'll show you later in some function block exercises why it matters. But okay, this is also less. So this is true. It's really shown well by that 1. This shows that it's a 1. And here we need an AND. And an AND means that you have to have 1s in all of these things to get a 1 out. That's going to matter in a second. We have this OR. So mainly we have a 1 here. And if we look at our expensive heater, it is on. Now, one thing I kind of don't like is I don't know, people look here and they don't associate this 1 with this. But this does. If you have a line going across here, this 1 is that right there. Okay, so now we're going to start heating. So that means our milliamp value is going to start going up. So there's 12, 12, 1. And we're going to bring it on up. Let me get it close. Let me get about 13.8. Okay, we see we're at 13.8. So at this point, notice this is a 0 now. Because 13.8 is not less than 12. So this is false. Now 13.8 is less than 14. So this is true. Now we have to have our expensive heater on. So we have an AND here. We have both 1s coming in. So we have a 1 here. So we have a 0 here, we have a 1 here, but this is an OR statement. So either or, if we got a 1 in one of these things, we're going to put a 1 out. And that's what we're showing here, our expensive heaters on. We're going to bump up to 14.1. And now we have 0 here, 0 here, 0 here, 0 here, 0 here. And so 14.9 or 14.1 is definitely greater than 12. So this is false. You see a 0. Same here. This is not less than this. So 0 here. And our expensive heater is not on now, mainly because this was false, this was false, And that made this false. So let's bump it back down. We're going to go back down to 13.9. So now this is true. Notice we got a 1 back here. That's why, I mean, function blocks has some advantages. But we need a 1 here and a 1 here to get a 1 out. So we're going to need, oops, going the wrong way. So we're going to need to get down. Let's get to a 12.1. And all right, 12.09, still not there. So I'm going to go to 11.9. And right away, we get a 1 here and everything's ready to go again. And we're going to cycle through this exactly the same as we cycled through with our ladder diagram. So they're going to do the exact same thing. And I had these set up down there where we had brighter things and we could have shown all of them at the same time, but you get the idea here. In fact, yeah, I can do a watch one day. So let's right click this and, oops, I wonder why they don't have the watch option there. But okay, at any point you can go to view and you can go to watch. And we're just going to drag, oops. Oh, I already have it down, that's right. We have a watch window that we don't really need our scale value. We'll leave that. Actually, we don't need either of these. But let's just delete that out. And let's drag this in. Oops, won't let me drag. So we're going to type local :1:0 dot data dot 0. That's one in our function block now. And we can copy that. We can put it right here and put 1. And that's going to be the other one. So now they're both off. And we're going to go up to, oops, down. We're going to go down to 12. They both kick on at exactly the same time. We got 1s in both of them. We come up. And they go back off. Now, one question is, should we use this? And this is some question I get often. And, you know, and I'm surprised nobody said it yet. This is horrible. Or, you know, I don't know. It may have been long enough that all of them were gone. But it is regional. And that's what I have to say about whether you should do discrete logic in function blocks or ladder. If you're going into a plant and every technician in there is trained in ladder, please make the things like the switches and stuff ladder. And I know we could say, well, they need to be trained better. Okay, maybe they do, but you're going into a plant that 99% of them only know ladder. You need to make that part ladder. Now we can do our process control, scaling, and all that in function block because they don't go bad. They're not going to do as much troubleshooting as those. But now if I'm in Europe, you know, and I'm kind of broadly saying Europe, I got to remember Europe's a huge place, but for the most part, Europe, you're going to see a lot more function blocks. And to a point, maybe if I throw ladder there, you may be in a place that 99% of them only know function blocks. So it's very regional. It's very important that you figure out, or you know your audience. I guess that's what I got to say. You got to know your audience. You know, you got to know who's going to work on the equipment. And no, there is no statement out there saying, oh, well, they just need to be trained better. No, no, trust me, I need people to go for training. I mean, we make a living off of training. But that is not an excuse for writing a program that can't be troubleshot by the bulk of the technicians at a plant. But okay, while we're here, let's go ahead and see how will we do this in structured text. Because we've spelled it out almost. Really, if you go back to our ladder here, we've said if the ladder, or let's say if the value is less than 12, or the ladder is less than 14, and the motor is running, or our pump is running, or our heater is running, whatever, then turn on the output. Oh, we can type that out in structured text. So if we go over here and we edit this, and yeah, we're going to go to the next line, and we're going to type if. And you start typing, and then you know all your instructions are going to come up. So if you're not sure, you know, there it is, if. And we can even mouse over it, and okay, if then, that's what we're doing. So we're going to double click there. And so the first thing was that our scaled, and okay, in this case we're going to use the scaled structured text, is greater than our MA. And remember, and this was cool. Even though it's structured text, I would always use the drop downs because I'm not a great typer. But our milliamp set point. So there's our first condition. Or, now let's make sure we get our parentheses right, is now we're just going to put or, and now I need a parentheses because same grouping we had to do in function block, we've got to do over here. So the and came first, and then we had the or. So order operation, this gets the parentheses to make sure that we evaluate it first. So or, and this will be scaled, function block, structured text. Oops, I made a mistake. Is that greater than, was that less than? Those were less thans. So less than, and this will be scaled structured text. Oops, lost my mouse, there we go. Is less than, and this was the MA off. And now we need that and we're just typing it out exactly like we would. And local colon, and we're going to change, we're going to change this so you can see the green light. So we are going to use local colon 1 dot data. Now remember, if you're going through this just like I am, then you're going to need to go back, just like I'm getting ready to do, and edit that other one. So if the scale structured text is less than milliamp, or the structured text level is less than milliamp off, and that, then, oops, actually, then I would put, no, I would put it that way probably. Which way would I do it? I don't even know how I would do it, but it's cool. You can put it anywhere. That's what's kind of terrifying about structured text. But, so if it's true, then we're going to make local colon 1 colon O dot data dot 0 colon equals, because remember, that's how we make it do something, 1 semicolon. Else, if, I said else, now notice there, I put else and I even paused for a second. It's like, which one is it? So we have an else and we have an else if. So we could have multiple conditions, but in this case, we're going to use the else, local colon 1 colon O dot data dot 0 colon equals 0 semicolon. And then we need an end if. And really, these should be lined up differently, and everybody has a different preference on this, and I don't know how I'll do it. I probably do that. Somebody else might say the indentation should be different, but I usually have a typo in this. So first, let's hit the verify button. Statement, line number 5, statement, there you go. I'm going to do it 90% of the time. I'm going to forget one of these semicolons. And so what this means, not terminated by a colon, line 5. So to tell you exactly where the problem is, I'm going to put that there. I'm going to hit my verify button again just to make sure. And we're looking good. Now let's go to that function block routine though. And let's edit it. And I changed the other one to a 1, so let's change this to a 2. And in this case, we'll change this to a 2. And that will do all that. All right, and now if we go to our structured text, and here's where you're at. Notice that while I was editing, I couldn't see the values. And I think they made a good compromise. I wish this was the default value, or maybe they just, I don't know. If you do not know that you can look at these values in structured text, it can be a nightmare to troubleshoot. But all right, we are at 14.3 milliamps. Uh-oh, what did I do wrong? I did something wrong here. Oh no, okay. Here's our scaling, that's our scaling. Here's where we're at. 14.3 has to be less than 12, or 14.3 has to be less than 14, and our output be on. Now one thing to notice is we don't have a description here, and I would knock people pretty hard on this. As you notice, if you go here, there's no way to actually put the descriptions in. So what you have is you can add descriptions to each line, and let's do that really quick. So I can go out here and I can go // and I can put that this is scaling analog input, and I can put / oh, determines if our, I don't know, what are we even calling this now? We're just going to call it our green light. Green light should be on. And then, yeah, this one's obvious probably, but I could throw something on it anyway. Turns green light on. And finally, this one's going to be turns green light off. All right. And let me put that in there because that's going to see these descriptions. And here's where, you know, structured text gets a bad rap because people don't use the tools available. And the one tool is these descriptions. The other is being able to see these values. And so, all right, Jason. Well, I'm glad you enjoyed this. And yeah, I think this is turned. I think we pieced this back together from a power failure, and we will make this available later. So make sure you're just subscribed, and you should be able to see that in the uploads later. Probably, and actually, it takes it a little time. It'll probably be like 24 hours before the whole thing's on YouTube. It takes a while to process the live streams. But okay, let's see if this works. So we're going to go down to 12, and we should see, well, one, we should see our green light come on. Then also right here, we should see this turn to a 1. And also if we bring our watch window back. Where did our watch window go? Did I close that? I think I did. Yes, I did. Let's go view, watch. And then let's add 5, since we did use 5 for the function block. So they're all off. I'm going to bring this down to 12.1. And, okay, and so this is looking for it to be less than 12, and it's off, and we see all of them are off here. We'll drop it to 11.9. Right away, all of these come on. And we can see, yeah, 11.9 is definitely less than 12, or 11.9 is less than 14. That's also true now. And the pump or whatever, the green light is now on. So both of these are true now. And, you know, I will not get too far into it, but I think this is still a little difficult to troubleshoot as far as turning on bits and things. So if you expect a technician to be able to go through the structured text, I think you better, you know, make sure that they are trained for it. It shouldn't be, they should be trained for it. But really, I would have this in either. It would again. It's regional. If it is ladder, then the physical outputs. Now, I use structured text all the time, and in fact, I'm going to critique one of my recent programs soon, where actually I use structured text, function blocks, and ladder diagram, and it wasn't intentionally. It was just the way the program worked out. But okay, let's go up to 14. Well, actually, let me bring it up to 13.9, and they're all ones. Now I'm going to bring up to 14.1, and we can see right here is what we're looking for. And that's going to go to 0. So this right here works exactly the same as this right here, which works exactly the same as this right here. So there are 3 ways that you can do this. Let's see, John, I like to put a structured text routine that is purely for, you know, I had never heard of doing this until recently. And I'm like, oh my goodness, why has no one ever told me to do that? So yeah, what John's saying is he adds a routine, and I'm going to call this machine document. Oh gosh. Yep. Time for the live stream to be over. I can't spell documentation now. Documentation. I'm hungry. And we're going to make a structured text. And then I'm going to open that up. And, oh, I always forget it. I have to right click it every time to see. Oops, not that. I want options. Right click. Options. Here you go. I don't remember all this that well. Oh, John, you're right there. What is it? Star? Is that how we add multi-line comments? Is that it? Oops, I gotta edit. That seems like that's not right. No. Anybody remember that? I know the / is the single line, and that's what I use most of the time, but there's a multi-line comment as well. And where is it? Oh, come on, computer. The computer is starting to choke too. It's like I'm done. Oh. Yeah, no, hold on. Let me, oh, come on, computer. Yeah, my computer is toast. There we go. Let's see. Oh gosh, I am not remember. There's a way to make multi-line comments. I should know that. Is it open parentheses? Oh, well, let's just try it. I probably could hit F1 too, but whoops, my mouse keeps disappearing over here. Parentheses, star, this. There we go. And mainly you can see that it's typing in green. So now I can put this is, whoops. I'm getting ready to hit my chat here. I remember the screens are backwards. This is one line of comment. And then this is another line of comment. And then at the end you put star parentheses. And then, isn't that it? Well, let's hit the button and find out. Yeah, there we go. So we're going to get a warning right now because machine documentation can't be reached. But here's where you can actually put, I mean, you could just, I mean, really, and that's what somebody was saying. Yeah, they have a manual that has some procedures in it. They copy and paste the whole procedure of how to do a couple things if you're having issues, some troubleshooting guides. So yeah, that's a really cool feature. And I haven't used it yet. I'm like, man, I can't wait to find a reason to do that. But okay, I think we have exhausted everything. Horribly not in order, but we have managed to get everything accomplished that we have. So let's wait a second and let me send Michael a message because Michael needs to select a winner here for our giveaway. So are there any other questions? Because yeah, we are getting ready to end this, and I do appreciate your patience as we completely changed what we did. We completely changed locations, scenes, equipment, and everything, and managed to still do this. But any last minute questions, and also be thinking what you want the next live stream to be about, and yeah, put it down in the comments because yeah, I've really enjoyed doing these. For one, I get a lot of immediate feedback on what you think. We got some great video ideas in them, and yeah. All right, and Michael. Come on, Michael. He's looking. We're waiting. I mean, Jeff, honestly, I don't ever use a linear. I use the switched, you know, that 60 watt class 2, the same thing you use. I don't, in this case, it doesn't matter. And I guess that's my answer to this. Is it doesn't really matter. But that's going to make a really good video, and I don't have the equipment to do it, but I'm going to show you on a milliamp setup, you can vary the signal. I mean, you can vary the voltage going into it, and it's still going to work great. That's what's awesome about milliamps, is it's going to regulate a current. As long as it has enough voltage to push 20 milliamp across that resistor, that load resistor, or their total network resistance, then it's going to work. And that's what's so cool about it. Okay, and the winner is John Birch. You have won the analog simulator. So John, if you will reach out to contact us at twcontrols.com, we'll get your address and get that worked out for you. And all right, guys, that is it for today. Again, please hit that subscribe button, like our channel, and yeah, any recommendations you have or questions, feel free to put them in the comments or reach out to me. And yeah, till next time. Hi, this is Tim.
And this is Amber of TW Controls. We run the automation store. Hey, thanks for finding our channel.
Here's a playlist with some similar videos.
And YouTube thinks you'll like this video.
Please like our video and subscribe to our channel.
And if our videos have helped you make some money and you're not using our products, please consider supporting us on Patreon.
Till next time.
See ya!